space where learning meets relaxation. Get comfortable, settle in, and let the gentle rhythm of this tutorial start to wash over you. Close your eyes if you like, or simply allow your mind to drift into a peaceful state. As we explore the world of our programming, may the words and concepts flow softly, guiding you through each step with ease. If you enjoy this journey, don't forget to like and subscribe for more relaxing coding tutorials. Let the calm begin. Welcome to this session on learning the R programming language and RStudio for data analysis. By the end of this course, you will gain a solid understanding of R and RStudio, set up your environment, and explore the basics of R syntax. R is a powerful tool for statistical computing and data science, and mastering it will open doors to a wide range of analytical opportunities. Whether you are a student, researcher, or professional, R is widely used across academia, research, and industry for tasks ranging from data cleaning to advanced statistical modeling. This course will guide you through the fundamentals, ensuring you build a strong foundation to tackle real-world data challenges. R is a programming language and environment specifically designed for statistical computing and graphics. It is open source, meaning it is free to use and modify, and it runs on multiple platforms, including Windows, Mac OS, and Linux. This flexibility makes R accessible to a broad audience. R is renowned for its extensive capabilities in data analysis, from basic calculations to complex modeling. Its strength lies in its vast ecosystem of packages, which extend its functionality. For example, the diverse collection of packages streamlines data manipulation and visualization, while ggplot2 allows for creating elegant and customizable plots. These tools make R a go-to choice for data scientists and statisticians worldwide. RStudio is an integrated development environment, or IDE, tailored for working with R. It provides a user-friendly interface that enhances productivity by organizing key features into separate panes. The code editor allows you to write and save scripts, while the console lets you execute commands interactively. The environment pane displays all your variables, data, and objects, making it easy to monitor your work. Additionally, the files, plots, packages, and help pane offer tools for managing files, visualizing results, installing new packages, and accessing documentation. RStudio is available as a desktop application and a cloud-based version, making it versatile for different workflows. To begin your journey with R, you need to install R first. Visit the Comprehensive R Archive Network, or CRAN, at cranrproject.org and download the appropriate version for your operating system. Once R is installed, proceed to install RStudio Desktop from POSIT. go/download/RStudio Desktop. This step-by-step process ensures that RStudio can communicate with your R installation. After installation, open RStudio and run the command R version in the console to verify that everything is set up correctly. This simple check confirms that R and RStudio are working together seamlessly. The RStudio interface is divided into several key panes that streamline your workflow. The script pane is where you write and save your R scripts, allowing you to keep your code organized for future use. The console pane is where you can execute commands directly, making it ideal for testing small snippets of code. The environment pane provides a view of all your variables, data frames, and objects, helping you track the state of your analysis. Finally, the files, plots, packages, and help pane serves as a central hub for managing files, viewing visualizations, installing new packages, and accessing comprehensive documentation. These features work together to make data analysis more efficient. In R, assigning values to variables is straightforward. You can use either the less than hyphen symbol or the equal sign, such as x less than hyphen 5 or x equal to 5. R supports various data types, including numeric for numbers, character for text, logical for true or false values, factor for categorical data, and list for storing mixed data types. Functions like print, sum, mean, and C short for combine are essential for performing operations. For instance, printx displays the value of x, while C1, 2, 3 creates a vector. Comments, denoted by the hash symbol, are used to annotate code and improve readability. These elements form the building blocks of R programming and are crucial for writing effective and maintainable code. R's power lies in its extensive collection of packages, which extend its functionality. The Tidyverse is a suite of packages designed for data science, including Deepler for data manipulation and ggplot2 for data visualization. The stats package provides built-in statistical functions, making it a core component for analysis. For machine learning, the Caret package offers tools for training and evaluating models. Additionally, the Shiny package enables the creation of interactive web applications, allowing users to share their analyses with others. These packages, along with many others, make R a versatile tool for tackling diverse data challenges. In summary, R is a cornerstone of statistical analysis and data science, and RStudio provides a powerful environment to work with it. By installing R and RStudio, practicing basic syntax, and exploring key packages, you will be well equipped to start your data analysis journey. In the next session, we will dive deeper into data manipulation and visualization techniques in R. Remember, the key to mastering R is consistent practice and curiosity. As you progress, you will discover how R can transform raw data into meaningful insights. Let's continue learning and exploring together. Good morning, everyone. Today, we will begin our journey into the world of R programming. This session will cover the basics of R and RStudio, why getting the installation right is crucial, and what we will explore together. By the end of this training, you will have a solid understanding of how to set up your environment and start using these powerful tools for data analysis. Let's start with an introduction to R and RStudio. Then move on to why proper installation matters. And finally, outline the agenda for our time together. R is an open source programming language specifically designed for statistical computing and graphics. It is widely used across industries, from academia to business, for tasks like data analysis, visualization, and even machine learning. What makes R unique is its extensive collection of packages, which extend its capabilities to almost any data-related task. However, R itself is a command line tool, which can be challenging for beginners. That's where RStudio comes in. RStudio is an integrated development environment that simplifies working with R by providing a user-friendly interface, making coding, debugging, and managing packages much more efficient. RStudio is an integrated development environment, or IDE. For R, an IDE is a software application that provides comprehensive tools for writing, testing, and debugging code. RStudio streamlines the coding process by offering features like a console for running commands, a script editor for writing code, and a package manager for installing and updating libraries. It is available in 2 versions: a free desktop version that you can install on your computer, cloud-based version that allows you to work from any device with an internet connection. Whether you prefer a local setup or remote access, RStudio has a solution for you. Before we dive into installation, let's discuss the system requirements. R and RStudio can run on Windows, Mac OS, or Linux, so there's no issue with operating system compatibility. However, your machine should have at least 2 gigabytes of RAM, though 4 gigabytes or more is recommended for smoother performance, especially when handling large datasets. An internet connection is also essential because many R packages are hosted online and require downloads. Make sure your system meets these requirements before proceeding to installation. To install R, the first step is to visit the official R website, which is cranrproject.org. From there, you'll find the latest version of R tailored for your operating system. Download the appropriate installer, and once it's ready, run the file and follow the on-screen instructions. The installation process is straightforward, but it's important to choose the correct version for your OS. If you're unsure, the website provides clear guidance. Once installed, R will be ready to use, but we'll need RStudio to enhance the experience. Next, we'll install RStudio. Head to the RStudio website at posit.co/download/RStudio desktop. Again, select the version that matches your operating system. The download will start automatically, and once it's saved, open the file to begin the installation. The setup wizard will guide you through the process, and it should take just a few minutes. After installation, RStudio will be ready to use, but we'll need to configure it to work with the R version we just installed. Once RStudio is installed, launch it to begin the configuration. The first time you open it, RStudio will attempt to detect your R installation automatically. If it fails, you can manually set the R path by going to Tools Global Options. This step ensures RStudio can communicate with R additionally. Take a few moments to customize your preferences, such as changing the theme to suit your visual comfort or adjusting keyboard shortcuts to match your workflow. These small tweaks can make a big difference in your daily use. Now that R and RStudio are installed, let's verify everything is working correctly. Open RStudio and check the R version in the console. Type R version and press Enter to confirm the installation. You should see detailed information about the R version and system configuration. To test it further, run a simple command like print hello R. If the console outputs the message, you've successfully set up your environment. This step is crucial to catch any issues early and ensure a smooth workflow. Despite following the steps, you might encounter some common installation issues. Firewalls or antivirus software can sometimes block downloads or installations, so temporarily disabling them might help. Another issue could be missing system dependencies, such as C++ compilers, which some R packages require. Lastly, conflicting software versions, like an outdated R version or incompatible RStudio, can cause problems. If you run into any of these, don't worry. We'll cover how to resolve them in the next slide. If you face any issues, start by checking the error messages in the logs. R and RStudio generate detailed logs that can help identify the problem. You can find these in the Help menu or by searching online for the specific error. If you're stuck, the RStudio community forums are a great resource where experienced users and developers can offer guidance. As a last resort, try reinstalling both R and RStudio. Sometimes, a fresh installation can resolve persistent issues. Remember, troubleshooting is part of the process, and you're not alone in this. To wrap up, R and RStudio are indispensable tools for anyone working with data. Proper installation ensures you can access the full range of features and packages without disruptions. Practice installing and configuring these tools to build confidence. As you progress, you'll find that a well-set-up environment makes all the difference in your productivity. Take the time to explore and experiment. Your journey into data analysis starts here. Thank you for joining me today, and I look forward to seeing your progress. Our programming language is known for its simple and intuitive syntax, which makes it accessible for users who are new to programming. The syntax is designed to be straightforward, allowing for easy data manipulation and analysis. Commands in R are typically written as functions, which are enclosed in parentheses. For example, when you want to calculate the mean of a set of numbers, you use the mean function with the values inside the parentheses. Assigning variables in R can be done using either the less than hyphen operator or the equal sign. However, it is important to note that R is case sensitive, meaning that variables like myvar and myvar are considered different. This case sensitivity is a crucial aspect of the language and helps prevent errors in variable naming. The basic syntax structure of R includes several key components. Assignment is a fundamental concept where values are stored in variables using either the less than hyphen or equal sign. For instance, x less than hyphen 10 or x equals sign 10 both assign the value 10 to the variable x. Arithmetic operations in R are performed using symbols like plus, minus, multiplication, division, and exponentiation. These operations allow for mathematical computations within the language. Logical operators such as equals, not equals, greater than, less than, greater than or equal to, and less than or equal to are used to compare values and return logical results. Vectors, which are one of the most basic data structures in R, can be created using the C function to combine elements, or using the colon operator to generate sequences. For example, C123 creates a vector containing the numbers 1, 2, and 3, while 1:5 generates a sequence from 1 to 5. Variables in R can hold different types of data, including numeric, character, and logical values. Numeric variables store numbers, such as integers or decimals, and are assigned using simple syntax like x less than hyphen 5. Character variables store text and are assigned by enclosing the text in quotes, such as name less than hyphen R programming. Logical variables hold Boolean values, either true or false, and are assigned using the keywords true or false. In addition to individual variables, R allows for the creation of vectors, which can contain multiple elements of the same data type. For example, numbers less than hyphen C123 creates a vector with the numbers 1, 2, and 3 matrices are another data structure that can be created using the matrix function, which takes a vector of values and arranges them into rows and columns. This versatility in data types makes R a powerful tool for data analysis. Functions in R are essential for performing operations and computations. Built-in functions, such as mean, sum, and length, are predefined in R and can be used immediately without any additional code. For example, the mean function calculates the average of a set of numbers. The sum function adds them up, and the length function returns the number of elements in a vector. In addition to built-in functions, users can define their own functions to perform specific tasks. A user-defined function is created using the function keyword, followed by the function name, and a set of parentheses containing the arguments. Inside the function, the code is enclosed in curly braces, and the return statement is used to specify the output. For instance, a function called myFunction can be defined to take an input x and return x squared. This ability to create custom functions enhances the flexibility and reusability of our code. Adding comments to our code is a best practice that helps improve readability and maintainability. Comments are created using the hash symbol, followed by the explanation or note. For example, a comment like this is a comment can be placed next to a line of code to explain its purpose. Comments are particularly useful for explaining complex operations or providing context for future readers of the code. However, it is important to avoid over-commenting, as excessive comments can clutter the code and make it harder to read. Instead, focus on adding comments where they provide meaningful insight, such as explaining the logic behind a particular calculation or the purpose of a function. Maintaining readability in our code is crucial for both personal and collaborative projects. One of the key practices is using consistent indentation, typically 4 spaces, to structure the code and make it easier to follow. Descriptive variable names, such as student score instead of x, help convey the purpose of the variable without needing additional comments. When dealing with complex operations, adding comments can clarify the intent behind the code and make it more understandable for others. Additionally, breaking long lines of code into shorter, more manageable segments can enhance readability. For example, instead of writing a single long line with multiple operations, it's better to split it into several lines, each focusing on a specific task. These practices contribute to writing clean, efficient, and maintainable R code. In conclusion, mastering the syntax and proper use of comments in R programming is essential for writing clear and effective code. By practicing with simple scripts and focusing on proper formatting, learners can build a strong foundation in R. Comments and readability are particularly important when working in teams, as they facilitate collaboration and reduce the likelihood of errors. As you continue to learn, exploring more advanced syntax and techniques will enable you to tackle complex tasks and enhance your data analysis capabilities. Keep experimenting and refining your skills to become proficient in R programming. Variables are essential tools in programming that allow you to store and manipulate data within your code. In R, you can create variables using assignment operators such as the left arrow symbol or the equals sign. For example, You might assign the number 10 to a variable called x by typing x left arrow 10 or y equals hello. It's important to note that variable names in R must start with a letter or a dot, which helps prevent conflicts with reserved keywords and ensures clarity in your code. This naming rule is a fundamental part of writing clean and readable R scripts. R has 6 primary data types that determine how data is stored and processed within the language. These include numeric, character, logical, integer, factor, and complex types. Each data type serves a specific purpose and influences how operations are performed on the data. For instance, numeric values can be integers or decimals, while character data is used for text. Logical values represent true or false states, and integer types are used for whole numbers. Factors are particularly useful for categorical data, and complex numbers are used for mathematical operations involving imaginary numbers. Understanding these data types is crucial for effective data analysis. In R, the numeric data type in R is used to represent real numbers, which can be either integers or decimals. This is the default type for numbers in R, meaning that when you enter a number without any special notation, it is automatically treated as numeric. For example, if you assign the value 25 to a variable called age, R will recognize it as a numeric type. Similarly, a variable like height can store a decimal value such as 5.9. Numeric data is fundamental for mathematical calculations and is widely used in statistical analysis. Character data types in R are used to store text strings, which are enclosed in either single quotes or double quotes. This flexibility allows you to choose the quote style that best fits your coding preferences or project requirements. For example, you might assign the name Alice to a variable called name using double quotes, or store the city New York in a variable called city using single quotes. Character data is essential for handling textual information, such as names, addresses, or any other non-numeric data you might encounter in your datasets. Logical data types in R are used to represent Boolean values, which can only be true or false. These values are crucial for performing conditional operations, such as checking if a certain condition is met. For instance, you might create a variable called isValid and assign it the value true, or use a comparison operator to determine if 5 is greater than 3, which which would result in true. Logical data types are the backbone of decision-making in programming and are often used in loops, if-else statements, and other control structures. Integer data types in R are used to store whole numbers, and they are distinguished from numeric types by the use of the letter L at the end of the number. For example, if you assign the value 10 to a variable called num, it will be treated as a numeric type by default. However, if you write num10L, R will recognize it as an integer. This distinction is important because integers are stored more efficiently in memory and are often used when working with counts or discrete values. Using the L suffix ensures that your data is stored in the correct format for specific operations. Factors in R are used to represent categorical variables, which have a fixed set of possible values known as levels. This data type is particularly useful in statistical analysis, as it allows you to group data into categories and perform operations like frequency counts or cross-tabulations. For example, a variable called gender can be converted into a factor with levels male and female, ensuring that R treats these categories as distinct and not as numerical values. Factors help maintain data integrity and are commonly used in datasets where variables have limited, predefined options. Vectors are the most basic data structure in R, designed to store multiple values of the same data type. You can create a vector using the combine function, which is denoted by the C symbol. For instance, numbers C1, 2, 3 creates a numeric vector containing the numbers 1, 2, and 3, while letters C, B, C creates a character vector with the letters. A B and C vectors are essential for performing operations on multiple values at once, making them a powerful tool for data manipulation and analysis. Matrices in R are two-dimensional data structures that organize data into rows and columns, similar to a spreadsheet. You can create a matrix using the matrix function, which requires a vector of values and specifications for the number of rows and columns. For example, mat matrix 1, 2, 3, 4. N row equals 2 creates a 2x2 matrix with the numbers 1, 2, 3, and 4. Matrices are useful for mathematical operations, such as matrix multiplication, and are often used in linear algebra and statistical modeling. Arrays in R extend the concept of matrices to 3 or more dimensions, allowing you to store data in a more complex structure. You can create an array using the array function, which requires a vector of values and a dimension vector specifying the size of each dimension. For instance, R array 1 24, dim equals C3 for 2 creates a three-dimensional array with dimensions 3, 4, and 2 arrays are particularly useful for storing and manipulating data that has multiple layers, such as time series data across different locations. Data frames in R are tabular data structures that resemble spreadsheets with rows and columns. Unlike matrices, which require all columns to have the same data type, data frames allow each column to have a different type, such as numeric, character, or logical. For example, you might create a data frame called DF that contains a column for names and another for ages. Data frames are widely used in data analysis because they can easily handle mixed data types and are compatible with many R functions for data manipulation and visualization. Lists in R are versatile data structures that can store elements of different data types, making them highly flexible for various programming tasks. You can create a list using the list function, which allows you to combine vectors, matrices, data frames, or even other lists. For example, mylist list A1 true creates a list containing a character, a numeric, and a logical value. Lists are particularly useful when you need to store heterogeneous data or when working with complex data sets that require multiple components. To summarize, R has several fundamental data types that serve different purposes in data manipulation and analysis. Numeric types handle real numbers. Character types store text. Logical types represent true or false values. And integer types are used for whole numbers. Factors are ideal for categorical data, while lists, vectors, matrices, and data frames are more complex structures for organizing and analyzing data. Understanding these types and their applications is essential for writing efficient and effective R code. In conclusion, variables and data types form the foundation of data manipulation in R, enabling you to store, process, and analyze information effectively. Choosing the appropriate data type ensures that your computations are both accurate and efficient, while practicing with variables helps reinforce your understanding of R's capabilities. By mastering these concepts, you will be well equipped to tackle more advanced topics in R programming and data analysis. Operators are symbols that perform operations on variables and values. For example, when you add two numbers or compare two pieces of data, you are using operators. Expressions are combinations of variables, constants, and operators that evaluate to a single value. Think of them as the building blocks of any calculation or decision-making process in R. Understanding operators and expressions is fundamental for data manipulation in R because they allow you to perform calculations, filter data, and create complex logic to analyze and transform datasets effectively. The arithmetic operators include addition, subtraction, multiplication, and division. These are the basic operations you use to perform calculations. For instance, adding two numbers with the plus symbol, subtracting one value from another with the minus symbol, multiplying values with the asterisk, and dividing with the /. Additionally, there are specialized arithmetic operators such as modulus, which gives the remainder of a division, and exponentiation, which raises a number to a power. For example, 3 plus 5 equals 8, 10 minus 2 equals 8, 4 multiplied by 2 equals 8, and 8 divided by 4 equals 2. Modulus can be used to check if a number is even or odd, and exponentiation can calculate squares or cubes. Comparison operators allow you to compare values and determine relationships between them. These include equality, which checks if two values are the same, and inequality, which checks if they are different. You can also use greater than, less than, greater than or equal to, and less than or equal to. For example, 5 equals 5 is true, 3 is greater than 2 is true, and 7 is less than or equal to 10 is also true. These operators are essential for filtering data, such as identifying values that meet specific criteria in a dataset. Logical operators are used to combine the results of comparisons. The AND operator, which can be represented by the ampersand or the double ampersand, returns true only if both conditions are true. The OR operator, represented by the vertical bar or the double vertical bar, returns true if at least one condition is true. The NOT operator, represented by the exclamation mark, inverts the truth value of a condition. For example, true and false is false. Not 3 is greater than 5 is true, and 5 is less than 10 or 2 is greater These operators are crucial for creating complex conditional statements in R. Assignment operators are used to assign values to variables. The most common is the left arrow, which is widely used in R for assigning values. The equal sign is also used, particularly in function arguments, to specify parameters. The double left arrow is used for assigning values to variables in the global environment, which is useful in functions. For example, x is assigned the value 10, y is assigned 5, and c is assigned 3 globally. Choosing the right assignment operator ensures that your code is clear and functions as intended. Special operators include the percent in percent, which checks if a value is present in a vector, and the percent star percent, which is used for matrix multiplication. The colon operator generates sequences of numbers, and the modulus operator, which is also used in arithmetic operations, calculates the remainder of a division. For example, the vector 1, 2, 3 is checked against the vector 2, 4 to see if any elements match, and the sequence 1 to 5 is created. These operators provide powerful tools for data manipulation and analysis. In R, an expression evaluates to a single value, which can be a number, a logical value, or a character string. Expressions combine operators, variables, and functions to perform tasks. For instance, 2 plus 3 multiplied by 4 evaluates to 14 due to operator precedence. The square root of 16 equals 4, and the mean of the vector 2, 4, 6 is 4. These examples demonstrate how expressions are used to perform calculations and derive insights from data. Operator precedence determines the order in which operations are performed in an expression. Parentheses take the highest priority, allowing you to override the default order. Exponentiation follows, then multiplication and division, followed by addition and subtraction. The colon operator for sequences comes next, then comparison operators, followed by logical operators. For example, 3 plus 5 multiplied by 2 evaluates to 13. Because multiplication takes precedence over addition. Understanding precedence ensures that your expressions are evaluated correctly. Practical examples of operators include combining them for complex calculations. For instance, the expression 10 plus 5 multiplied by 2 divided by 3 simplifies to 10. Logical operators are used to filter data, such as selecting rows where the age is greater than 30 and gender is female. The colon operator generates sequences like 1 to 10 in steps of 2. These examples illustrate how operators are applied in real-world scenarios to manipulate and analyze data efficiently. Operators and expressions form the building blocks of our programming, enabling you to perform calculations, make decisions, and transform data. Mastering them allows you to write efficient and effective code for data manipulation and analysis. Practice using operators in real-world scenarios to reinforce your understanding and become proficient in R programming. By applying these concepts, you can unlock the full potential of R for data science tasks. Matrices and arrays are fundamental data structures for multidimensional data. They allow us to organize and manipulate data in a structured way, which is essential for tasks like statistical analysis, linear algebra, and data manipulation. In R, a matrix is specifically a two-dimensional structure, meaning it has rows and columns, while an array extends this concept to 3 or more dimensions. This makes arrays particularly useful for handling complex datasets, such as those encountered in image processing or scientific research. Understanding how to create and work with these structures is a critical skill for anyone looking to perform advanced data analysis in R. To create a matrix in R, we use the matrix function. The basic syntax is matrix data, nrow, ncol, byrow equals false. The data argument can be any vector, and the nrow and ncol parameters define the number of rows and columns in the matrix. By default, the matrix fills data column-wise, which means it starts with the first column, then moves to the next. If you want to fill the matrix row-wise, you can set byrow to true. For example, if you have a vector of numbers and specify 2 rows and 3 columns, the matrix will arrange those numbers vertically first. This flexibility allows you to structure your data in a way that suits your analysis needs. For arrays, the function to use is array. The syntax is array data. dim equals c n1, n2, n3, and so on. Here, the dim argument specifies the dimensions of the array, which can be 3 or more. For instance, if you have a vector of numbers and set dim to C2, 3, 4, you create a 3-dimensional array with 2 layers, 3 rows, and 4 columns. Like matrices, arrays fill data column-wise, but this behavior applies across all dimensions. This makes arrays ideal for storing data, that requires multiple indices, such as temperature readings across different locations, times, and depths. Indexing matrices allows you to access specific elements or subsets of the matrix. The notation is row, column, where you specify the row and column numbers. For example, to get the element in the second row and third column, you would write matrix 2. 3. You can also extract entire rows or columns by omitting the second or first index, respectively. For instance, matrix row would give you the entire row, while matrix column would give you the entire column. Additionally, you can use logical or numeric indices to subset the matrix, which is useful for filtering data based on certain conditions. This level of control makes matrices a powerful tool for data manipulation. Indexing arrays extends the concept of matrices to multiple dimensions. The notation becomes dim1, dim2, dim3, where each index corresponds to a specific dimension. For example, in a three-dimensional array, you might use array 1 to extract the first layer across all rows and columns. When subsetting arrays, it is important to use the drop equals false argument to ensure that the resulting object remains an array rather than being simplified to a lower dimension. This is particularly useful when you need to maintain the structure of your data for further analysis or visualization. Matrix operations in R include a variety of arithmetic and algebraic functions. You can add, subtract, multiply, or divide matrices using the standard operators plus, minus, star, slash. However, matrix multiplication requires the special operator %, which performs the correct linear algebra operation. Other functions include T for transposing a matrix and solve for inverting it. You can also combine matrices using C-bind to add columns or R-bind to add rows. These operations are essential for tasks like solving systems of equations or preparing data for machine learning models. Understanding how these functions work will enhance your ability to analyze and transform data efficiently. Array operations are similar to matrix operations, but are designed for higher dimensional data. The apply function is particularly useful for applying a function across specific dimensions of an array. For example, apply array 1. Mean would calculate the mean for each row across the first dimension. This allows you to perform complex calculations on multi-dimensional datasets without manually looping through each element. By specifying the margin or margin, you can control which dimensions the function operates on. This flexibility makes arrays a versatile tool for handling data in fields like genetics, where datasets often have multiple layers of information. Several functions help you work with matrices and arrays in R. The dim function returns the dimensions of an array, while nrow and ncol give the number of rows and columns in a matrix. To check if an object is a matrix or array, you can use isMatrix and isArray. Additionally, the replicate function allows you to create arrays with repeated values, which can be useful for generating test data or simulating scenarios. These functions provide the tools needed to inspect, validate, and manipulate your data structures, ensuring they are correctly formatted for analysis. Matrices and arrays are essential for organizing multidimensional data efficiently, making them a cornerstone of data analysis in R. By mastering indexing and operations, you can unlock the full potential of these structures to perform complex tasks. Whether you are working with statistical models, linear algebra problems, or multidimensional datasets, practice is key to becoming proficient. As you apply these concepts to real-world scenarios, you will find that matrices and arrays become indispensable tools in your data science toolkit. Keep experimenting with different functions and datasets to reinforce your understanding and improve your skills. A data frame is a two-dimensional structure that organizes data into rows and columns. Think of it like a spreadsheet or a database table, where each row represents a unique observation and each column represents a specific variable. For example, if you have a data set of students, each row might represent a student, and columns could include their names, ages, and grades. What makes data frames powerful is their ability to hold different types of data in separate columns. One column could be numeric, like age. Another could be character, like names. And another could be a factor, like gender categories. This flexibility makes data frames ideal for storing and analyzing tabular data, which is common in fields like statistics, data science, and research. To create a data frame in R, you can use the data frame function. For example, if you want to create a simple data set with names and ages, you might write df less than or equal to data frame name equals C Alice Bob and age equals C 2530. This will generate a data frame with two columns columns and 2 rows. But data frames aren't limited to manually entered data. You can also read data from external files like comma-separated value files using the read CSV function. This is especially useful when working with large data sets that are stored in files. The read CSV function automatically converts the file into a data frame, making it easy to start analyzing the data right away. In a data frame, each row represents an observation, and each column represents a variable. For instance, if you have a data set about cars, each row might be a specific car model, and the columns could include variables like horsepower, weight, and fuel efficiency. It's important that column names are unique and descriptive so that you can easily reference them later. Data frames support mixed data types, which means one column can be numeric, another can be character, and another can be logical. This is different from some other structures in R that require all elements to be the same type. To add new columns to a data frame, you can use functions like cbind, which combines columns, or mutate from the deepler package, which allows you to create new variables based on existing ones. Tibbles are modern alternatives to data frames that come from the Tidyverse package. They are designed to be more consistent and user-friendly for contemporary R workflows. You can create a tibble using the tibble function or by converting an existing data frame with as-tibble. Unlike data frames, tibbles are built with the principles of tidy data in mind, which means they prioritize clarity and simplicity. For example, tibbles avoid some of the quirks of data frames, like automatically converting character vectors to factors. This makes them particularly useful when working with data that requires precise type control. Tibbles have several key features that set them apart from traditional data frames. First, they preserve the original data types of the input. So if you have a column of strings, it will stay a character vector instead of being converted to a factor. Second, when you print a tibble, it only displays the first 10 rows and columns, which helps prevent overwhelming the user with large data sets. This is especially helpful when working with big data. Tibbles also use the tibble class instead of the data frame class, making it easier to distinguish between the two structures. Finally, tibbles handle large data sets and nested data more efficiently, which is useful for advanced data analysis tasks. When comparing data frames and tibbles, it's important understand their strengths and weaknesses. Tibbles are generally more user-friendly for modern R workflows because they avoid some of the automatic type conversions that can cause issues. For example, data frames often convert character vectors to factors, which can be confusing. Tibbles, on the other hand, keep data types as they are unless explicitly changed. Data frames are older and more widely used in legacy code, so you might encounter them in older projects. However, tibbles offer better support for complex data types, like lists or functions, in certain cases. This makes them a better choice for projects that require more flexibility and control over data structures. There are several common operations you can perform on both data frames and tibbles. To subset rows or columns, you can use the bracket notation, which is part of base R, or the more readable functions from Deepler, like filter and select. Adding new columns is straightforward with mutate from Deepler or cbind, which combines columns. For summarizing data, functions like summary provide quick overviews, while Deepler's summarize allows for more customized aggregations. When merging datasets, you can use the merge function or Deepler's join functions, such as inner join or left join, depending on your needs. These tools make it easy to manipulate and analyze data, whether you're working with small datasets or large, complex ones. In summary, data frames are the foundational structure for tabular data in R, and they remain widely used in many applications. Tibbles, on the other hand, offer enhanced functionality and readability, making them ideal for modern workflows. The choice between the two often depends on the specific requirements of your project and your familiarity with the Tidyverse ecosystem. Practicing with both structures will help you become more versatile in data analysis. By understanding their differences and strengths, you can make informed decisions about which to use in different scenarios. Remember, the key to effective data analysis is not just knowing the tools, but also knowing when and how to use them. Lists are R's most flexible data structure. Unlike vectors, which can only hold elements of the same type, lists can store a wide variety of data. This includes vectors, data frames, other lists, and even functions. This flexibility makes lists ideal for handling complex data that doesn't fit neatly into a single type. For example, you might have a list that contains a numeric vector, a character string, and a data frame all in one place. This ability to combine different data types is what sets lists apart from other structures in R when you need to organize data that has multiple components or hierarchical relationships. Lists are the go-to solution. They allow you to create nested structures, which are essential for real-world data analysis, where information is often interconnected and multifaceted. To create a list in R, you use the list function. For example, my list less than or equal to list 1, text, true creates a list with 3 elements: the number 1, the text string, and the logical value true. This is a basic example, but lists can also have named elements. For instance, my list less than or equal to list A equals 1, B equals text, C equals true assigns names of B and C to the elements, making them easier to reference later. When you need to combine existing objects into a list, such as a vector, a data frame, or another list, you can pass them directly into the list function. This is useful when you want to group related data together for analysis or storage. For example, my list less than or equal to list vector 1, df 1, list 2 would create a list containing 3 separate objects, each of which could be of a different type. This method helps keep your workspace organized and your code efficient. Accessing elements in a list requires using different operators depending on the context. The double bracket operator is used to extract a single element from a list. For example, my list double bracket 1 would return the first element of the list. If the list has named elements, you can use the $sign operator, like my list A, to access the element named A. This is particularly useful for readability and simplicity. Another option is the single bracket operator, which returns a sublist containing the specified elements. For instance, my list 1, 2 would return a sublist with the first and second elements. When working with nested lists, you can chain these operators together. For example, my list double bracket 1 2 would access the second element of the first sublist. These tools provide the flexibility needed to navigate and manipulate complex data structures effectively. Lists are particularly powerful for storing and organizing complex data because they can contain multiple types of elements and nested structures. For example, a list might include a numeric vector, a character string, a data frame, and even another list, all within a single object. This allows you to group related data together making it easier to manage and analyze. In practical scenarios, this could mean storing a dataset with different variables, such as a vector of ages, a vector of names, and a matrix of measurements, all in one place. Lists also support hierarchical organization, which is useful for projects with layered data. For instance, a list could contain multiple sublists, each representing a different dataset or analysis step. This structure helps maintain clarity and reduces the risk of data fragmentation. By leveraging lists, you can create more structured and manageable code, especially when dealing with large or multifaceted datasets. Modifying or updating elements in a list is straightforward. To change an existing element, you can use the double bracket operator to assign a new value. For example, my list double bracket 1 double bracket less than or equal to new value would replace the first element of the list. If the list has named elements, you can also use the $sign operator, like my list, a less than or equal to new value. To update the element named A, adding new elements to a list is equally simple. You can use the double bracket operator with an index or the $sign with a new name. For instance, my list double bracket 4 double bracket less than or equal to new element adds a fourth element to the list, while my list new name less than or equal to new value assigns a new element with the name new name. These operations make lists highly dynamic and adaptable to changing data requirements. Combining lists is a common task in R, and the seep function is the primary tool for this. The seep function concatenates lists, adding their elements together. For example, combined list less than or equal to C list 1, list 2 would merge the elements of list 1 and list 2 into a single list. This is useful for aggregating data from multiple sources or merging results from different analyses. When combining lists, you can also add new elements directly. For instance, combined list less than or equal to C list 1, new element would append the new element to the end of the list. This flexibility allows you to build and expand lists incrementally, making them a versatile choice for data management. By using the seep function, you can efficiently combine and manipulate lists to suit your specific needs. When working with lists, it's often necessary to apply functions to their elements. The Lapley function is particularly useful for this, as it applies a function to each element of a list and returns a list of results. For example, Lapley myList, function would apply the specified function to every element in the the list. This is ideal for tasks like transforming data, calculating statistics, or performing operations on each component of a list. The Saply function is similar, but simplifies the output, returning a vector or matrix instead of a list. This can be helpful when you need a more compact result. Additionally, the unlist function converts a list into a vector, which is useful for further processing. These functions make it easy to work with lists in a programmatic and efficient manner, allowing you to automate complex operations and streamline your workflow. Functions in R are like reusable blocks of code that perform specific tasks. Think of them as tools that help you avoid writing the same code over and over again. They make your code more efficient, easier to read, and organized into manageable parts. R has a lot of built-in functions like mean and sum, which are ready to use. For example, mean calculates the average of a set of numbers, and sum adds them up. But you can also create your own functions, which is super powerful. To define a function in R, you use the function keyword. So, if you want to create a function that adds two numbers, you would write something like add functiona b a plus b, and then call it with add 2, 3 to get 5. This flexibility allows you to tailor functions to your specific needs. Arguments are the inputs that you pass to a function. They allow the function to work with different data or configurations. For example, if you have a function that calculates the mean of a dataset, you can pass different datasets to it by changing the arguments. Arguments can be positional, meaning you provide values in the order they are expected, or named, where you specify the parameter name along with the value. This makes your code more readable, especially when there are many arguments. Some arguments even have default values, which means if you don't provide them, the function will use a predefined value. For instance, in the mean function, the NARM argument has a default value of false. If you don't specify it, the function will include missing values in the calculation. But if you set NARM to true, it will ignore them. This flexibility makes functions more versatile. Parameters are the variables listed in a function definition, while arguments are the actual values you pass when calling the function. For example, if you define a function called add with parameters a and b, like add functiona b a plus b, then when you call add 2, 3, the values 2 and 3 are the arguments. Parameters act as placeholders that get replaced with the arguments when the function runs. This separation between parameters and arguments is crucial because it allows the same function to handle different inputs. Imagine if you had to rewrite the addition logic every time you wanted to add two numbers. That would be inefficient. Instead, functions let you define the logic once and reuse it with different arguments. There are several types of arguments in R, each with its own use case. Positional arguments are the simplest, where the order of the values you pass matters. For example, if a function takes length and width, you must provide them in that order. Named arguments, on the other hand, let you specify the parameter names along with the values, which makes your code clearer and less error-prone. For instance, instead of writing rectangleria 5, 10, you could write rectanglery length equals 5, width equals 10, which is easier to understand. Default arguments are values that the function uses if you don't provide them. This is useful for optional parameters. For example, a function might have a default value for a parameter that's rarely changed. Lastly, variable arguments allow a function to accept a variable number of inputs, which is handy for functions like paste or cat that can take multiple arguments. This flexibility makes functions more adaptable to different scenarios. Let's look at an example of a function. In R, suppose you want to calculate the area of a rectangle. You can define a function called rectangleria that takes two parameters, length and width. The function would multiply these two values and return the result. So the code would be rectangleria, function length, width, return length times width. When you call this function with rectangleria 5, 10, it will multiply 5 by 10 and return 50. This is a simple yet powerful example of how functions can encapsulate logic for reuse. Imagine if you needed to calculate the area of multiple rectangles in your code. Without a function, you'd have to write the multiplication each time, which is tedious and error-prone. With a function, you just call it with the appropriate values, making your code cleaner and more efficient. When writing functions in R, there are some best practices to follow. First, keep functions focused on a single task. A function should do one thing well, which makes it easier to test, debug, and reuse. For example, a function that calculates the area of a rectangle should not also plot the rectangle. Second, use descriptive names for functions and arguments. Instead of calling a function calc, name it something like rectangleria to make its purpose clear. Third, document your functions with comments or tools like Roxygen 2. This helps others understand how to use your functions and what they do. Finally, avoid side effects by ensuring functions return values instead of modifying global variables. Side effects can lead to unexpected behavior, especially in larger programs. By following these practices, your code becomes more maintainable and collaborative. Functions are a cornerstone of R programming, enabling you to write modular, efficient, and reusable code. Whether you're using built-in functions or creating your own, understanding how to define and use functions is essential. By breaking down complex tasks into smaller, manageable functions, you can tackle problems more effectively. Remember to leverage different types of arguments, follow best practices, and always aim for clarity and simplicity. As you gain more experience, you'll find that functions become an indispensable part of your workflow, making your code not only more powerful, but also easier to read and maintain. Control structures in R are essential tools that allow programmers to make decisions and repeat actions within their code. These structures enable programs to behave dynamically, adapting their execution based on specific conditions. By using control structures, you can create more flexible and powerful scripts that respond to different scenarios. The two main components of control structures are if-else statements, which handle decision-making based on logical conditions, and loops, which manage repetitive tasks. Understanding these elements is fundamental to writing efficient and effective R code. If-else statements are the building blocks of conditional execution. In R, they allow your code to choose between different paths based on whether a condition is true or false. The syntax for an if-else statement is straightforward. You start with the keyword if followed by a condition in parentheses. If the condition evaluates to true, the code block within the curly braces is executed. If not, the else block is executed instead. For example, if you have a variable x and you want to check whether it is greater than 10, you can write an if-else statement that prints high. If the condition is met and low otherwise. This structure is incredibly useful for handling binary decisions in your programs. When dealing with multiple conditions, the else if statement becomes invaluable. It allows you to check additional conditions sequentially, providing a way to handle more complex decision-making scenarios. For instance, You might use a series of else if clauses to evaluate a score and assign a corresponding grade. Additionally, nested if else statements enable hierarchical logic, where one condition is checked inside another. This is particularly useful when you need to evaluate multiple layers of dependencies. For example, a nested if else could first check a student's overall score and then evaluate their performance in specific subjects. Mastering these structures allows you to create highly customized and responsive code. For loops are designed to repeat a block of code a specific number of times, making them ideal for tasks that require iteration. The syntax of a for loop involves a variable that takes on each value in a sequence, such as a range of numbers or elements in a vector. As the loop progresses, the code within the curly braces is executed for each value in the sequence. A simple example is a loop that prints numbers from 1 to 5. This structure is particularly useful when you need to perform the same operation on multiple data points, such as calculating the sum of elements in a vector or applying a function to each item in a list. For loops are a cornerstone of automation in R programming, while loops are another type of loop that continues executing a block of code as long as a specified condition remains true. Unlike for loops, which iterate over a fixed sequence, while loops are ideal for situations where the number of iterations is not known in advance. The condition is evaluated before each iteration, and if it is true, the code block runs again. For example, a while loop could be used to increment a counter until it reaches a certain value. This flexibility makes while loops particularly useful in scenarios where the loop's termination depends on dynamic or user input. However, care must be taken to avoid infinite loops by ensuring the condition eventually becomes false. The break and next statements provide additional control over loop execution. The break statement immediately exits a loop, regardless of whether the loop's condition is still true. This is useful when you want to terminate a loop early based on a specific event. The next statement, on the other hand, skips the current iteration and proceeds to the next one. For example, if you are iterating through a list of numbers and want to skip a particular value, you can use next to bypass it. These statements allow for more granular control over loops, enabling you to handle exceptions or optimize performance by avoiding unnecessary iterations. When working with control structures, there are several common pitfalls to be aware of. One of the most frequent issues is infinite loops, which occur when a loop's condition never becomes false. This can happen due to a typo in the condition or an incorrect update of the loop variable. Another common problem is off-by-one errors, which arise when the loop's range is slightly incorrect, leading to either missing elements or processing them multiple times. Additionally, misusing logical operators can lead to unexpected results. For example, using the vectorized operator and instead of the scalar operator, and it can cause issues when working with conditions that involve multiple logical values. Being mindful of these pitfalls helps ensure that your code runs smoothly and efficiently. To write clean and effective R code, it is important to follow best practices when using control structures. First, keep your conditions simple and readable by breaking complex logic into smaller, manageable parts. This makes your code easier to understand and maintain. Second, whenever possible, use vectorized operations instead of loops, as they are often faster and more efficient in R. Finally, add comments to explain the purpose of complex logic, especially when using nested conditions or intricate loop structures. These practices not only improve code quality, but also make collaboration and debugging more straightforward. Control structures are the backbone of dynamic and responsive R programs. They allow you to make decisions and automate repetitive tasks, making your code more versatile. The FL structure is essential for conditional execution, enabling your programs to respond to different scenarios. For loops and while loops, on the other hand, automate repetitive actions, whether you know the number of iterations in advance or not. Together, these elements form the foundation of program flow in R, allowing you to create powerful and efficient scripts. Mastering them is a critical step in becoming proficient in R programming. In conclusion, control structures are indispensable tools for any R programmer. By mastering FL statements, loops, and their associated commands, you can write more efficient and dynamic code. Practice is key to developing proficiency, so try implementing nested conditions and loops in real-world scenarios to reinforce your understanding. Always remember to test your code thoroughly to catch logical errors and prevent issues like infinite loops. With consistent practice and attention to detail, you will be well on your way to writing robust and effective R programs. Strings in R are sequences of characters used to store text data, such as names, addresses, or any textual information. In R, you can represent strings using either double quotes or single quotes, which gives flexibility depending on the context. Common operations include combining strings, extracting parts of them, and transforming their case or format. For example, the paste function allows you to combine multiple strings into one, while subster helps extract specific sections of a string. Built-in functions like grep are useful for searching patterns within strings, making them essential tools for data analysis and text processing. Basic string operations in R include concatenation, which is the process of joining strings together. The paste function is often used for this, and it adds a space between the concatenated elements. For instance, paste hello world would result in hello world. If you want to join strings without any space, you can use paste 0 instead. Substring extraction is another key operation, achieved using the subster function. For example, subster R programming. 1 would return the first character R. Additionally, the nchar function helps determine the length of a string, which is useful for tasks like validating input or formatting output. R provides several functions for handling strings effectively. Case conversion is straightforward with tolower and tuper, which transforms strings to lowercase or uppercase, respectively. This is particularly useful when standardizing text data. The trimwas function removes leading and trailing whitespace, which is essential for cleaning up user inputs or imported data. Splitting strings is another common task, and the strsplit function allows you to divide a string into a list of substrings based on a specified delimiter. For example, splitting a BC by a comma would result in a list containing a B and C. These functions streamline the process of working with text data in R. Advanced string manipulation in R relies heavily on regular expressions, which are patterns used to match and modify text. Functions like grep and grepl are used to search for these patterns within strings. For instance, grep pattern X returns the indices of elements in X that match the pattern, while grepl returns a logical vector indicating matches. The sub and gsub functions are used to replace parts of strings. For example, G sub A, X, banana replaces all occurrences of A with X, resulting in BXNXX. Regular expressions allow for powerful text processing, making it easier to handle complex data cleaning tasks. Special characters in R require careful handling. For example, the backslash character is used as an escape character to represent symbols like newlines \n or tabs \t. However, when working with these in R, you need to use 2 backslashes to ensure they are interpreted correctly. Raw strings introduced in R410 allow you to avoid escaping by using the R. Syntax, which is particularly useful when dealing with complex patterns or file paths. The cat function is helpful for printing strings with special characters, as it can handle newlines and other formatting directly. Understanding these concepts is crucial for working with text data that includes non-standard characters. String formatting in R is essential for converting numerical data into readable text. The format-C and sprint functions are commonly used for this purpose. For example, sprint value %2f 3.1415 converts the number 3.1415 into the string value 3.14. Padding is another important aspect of formatting, where you add spaces or characters to align text. The strpad function from the stringer package allows you to pad strings to a specified width, which is useful for creating consistent output in reports or tables. These tools ensure that your data is presented clearly and professionally. Regular expressions in R are a powerful tool for pattern matching and text manipulation. Basic patterns include the dot, which matches any character, the asterisk, which matches 0 or more repetitions of the preceding element, and the plus, which matches 1 or more repetitions. Character classes, like a Z, match any lowercase letter, while \D matches digits. These patterns can be combined to create complex searches, such as finding all email addresses in a dataset. Understanding regular expressions allows you to perform sophisticated text analysis, making it a valuable skill for data scientists and analysts. Practical examples demonstrate the power of string manipulation in R. For instance, extracting email domains can be done using sub@. user@example.com, which removes everything from the @ symbol onward, leaving user. Cleaning data often involves removing non-alphanumeric characters, as shown by G sub Azazi. Hello 123, which results in hello. Splitting CSV data with SDR split ABC creates a list of A, B, and C. These examples highlight how string functions can be applied to real-world problems, making data processing more efficient and accurate. Common pitfalls in string operations include forgetting to escape backslashes in regular expressions, which can lead to unexpected results. For example, a literal backslash requires 2 backslashes in R. Misusing paste and paste 0 is another issue, as paste adds spaces between elements while paste 0 does not. Case sensitivity in regular expressions can also cause problems, as A and A are treated as distinct. Additionally, handling null values in string operations requires caution, as functions like subster may return null if the input is missing. Being aware of these issues helps avoid errors and ensures reliable results. Mastering string operations in R is crucial for effective data cleaning and analysis. Functions like gsub, str split, and regular expressions enable complex text processing tasks, making it easier to work with unstructured data. Practice with real-world datasets is essential to build proficiency, as it allows you to apply these tools in practical scenarios. Exploring packages like Stringer further enhances your capabilities, offering additional functions for advanced string manipulation. By developing these skills, you can significantly improve the quality and efficiency of your data analysis workflows. Understanding date and time data in R is essential for time series analysis and data manipulation. Whether you're working with financial data, environmental measurements, or social media activity, temporal data is a critical component of many datasets. R provides specialized classes and functions to handle dates and times efficiently, allowing you to perform tasks like calculating durations, extracting specific components, or aligning data across different time zones. This session covers core concepts, tools, and best practices for working with temporal data, ensuring you can confidently manage and analyze time-based information in your projects. The key date and time classes in R include date, POSI XCT, and POSI XLT. The date class represents calendar dates without any time component, such as 2020-31005. The POSI XCT and POSI XLT classes handle date time with time zones. For example, 2020-310, 5:14:30, 00 UTC. POSI XCT stores date time as the number of seconds since the Unix epoch, making it efficient for computation, while POSI XLT stores it as a list of components, which is useful for extracting specific parts like year or hour. Additionally, the Lubridate package offers intuitive functions to simplify date-time operations, making it easier to parse, manipulate, and format temporal data. Creating dates and times in R can be done using several functions. The asDate function converts character strings into date objects. For instance, asDate 2023-10-05 will return a date object for that day. To get the current date, you can use sysDate, which returns the system's current date. For the current date time, sysTime provides the system's current timestamp, including hours, minutes, and seconds. These functions are fundamental for tasks like logging events, tracking timelines, or generating dynamic data. For example, combining sysDate with asPOSI XCT allows you to create a date-time object with the current time. Formatting dates and times in R is achieved using the format function, which allows you to specify the output format. Common format codes include %Y for the 4-digit year, %M for the 2-digit month, %D for the 2-digit day, %H for the hour in 24-hour format, and %M for the minute. For instance, format sysDate, %Y, %M, %D will return the current date in a standard format. This flexibility is crucial for presenting data in user-friendly ways or ensuring compatibility with external systems that require specific date-time formats. Experimenting with different codes helps you tailor the output to your needs. Parsing dates and times involves converting character strings into date-time objects. The strTime function is used for this purpose, requiring a format string that matches the input. For example, strTime 2023-10-0, 5:14:30, 00. %Y, %M, %D, %H, %M, %S will parse the string into a date-time object. This is particularly useful when importing data from files or APIs that store dates in text format. In Ensuring the format string aligns with the input is critical, as mismatches can lead to errors or incorrect data. Tools like Lubridate's Parse Data Time can handle multiple formats automatically, reducing the complexity of parsing inconsistent data. Manipulating dates and times in R involves adding or subtracting intervals, extracting components, or comparing timestamps. The Lubridate package provides functions like days, weeks, months, and years to easily add or subtract time units. For example, today plus days 5 would give the date 5 days from now. Extracting components such as the year, month, or hour is straightforward with functions like year, month, and hour. These operations are essential for tasks like calculating age, determining the duration between events, or grouping data by specific time intervals. Combining these tools with base R functions enhances your ability to analyze temporal data effectively. Handling time zones in R requires attention to the TZ argument in functions like as POSI XCT, which allows you to specify the time zone. For instance, as POSI XCT 2023-10-0-5-1430-00 TZ equals UTC ensures the timestamp is interpreted in the coordinated universal time zone. The SIZ time zone function can be used to check the system's current time zone. When working with data from multiple regions, converting between time zones is vital. The widths function from Lubridate lets you change the displayed time zone without altering the underlying timestamp, while Forsets adjusts the time zone without changing the actual time. This distinction is crucial for accurate time-based analysis. Common challenges when working with dates and times include inconsistent date formats, time zone errors, and daylight saving time transitions. Inconsistent formats can be addressed using Parse Data Time from Lubridate, which automatically detects multiple possible formats. Time zone errors often arise from not specifying the TZ argument, so always explicitly define time zones to avoid misinterpretation. Daylight saving time changes can complicate calculations, but Lubridate's functions handle these transitions seamlessly, ensuring your analysis remains accurate even during time shifts. Being proactive about these issues improves the reliability of your temporal data workflows. Mastering dates and times in R enhances your data analysis capabilities, enabling you to work with time-based data more effectively. Built-in functions like as date, format, and SDR time provide a solid foundation, while the Lubridate package offers advanced tools for simplifying complex operations. Practicing parsing, formatting, and manipulating temporal data will prepare you for real-world applications, such as analyzing trends over time, scheduling tasks, or processing event logs. By understanding the nuances of date-time handling, you'll be equipped to tackle a wide range of data challenges with confidence and precision. Data import is the foundational step in any data analysis project. Without properly loading data, we cannot proceed to explore, clean, or analyze it. The most common file formats you will encounter are CSV files, which use commas to separate values, and Excel files, which can contain multiple sheets with structured data. R provides a suite of functions to handle these formats, making it easy to bring external data into your workspace. By the end of this session, you will learn how to load data from CSV and Excel files, manipulate it, and save your results in these formats. This skill is essential for working with real-world datasets, which often come in these file types. To read CSV files in R, the primary function is read CSV. The basic syntax is read CSV file path, header equals true, sep equals. The header argument tells R whether the first row contains column names, and the sep argument specifies the delimiter used in the file. For example, if your CSV uses semicolons instead of commas, you would set sep. The default for header is true. So if your file has headers, you can omit that parameter. A simple example is data read. CSV data, CSV, which loads the data into a variable called data. This function is straightforward but powerful, and it's the go-to tool for most CSV files. Once you have processed your data, you can save it back to a CSV file using the right CSV function. The syntax is write CSV data, output CSV, row names equals false. The row names argument determines whether to include row numbers in the output. Setting this to false is usually preferred, as it avoids unnecessary columns in the file. For instance, write CSV data, output CSV will save the data to a file named output CSV without row names. This is useful for sharing data with others or for further processing in other programs like Excel or Python. Reading Excel files requires a different approach, as R does not natively support Excel formats. Instead, we use the Read Excel function from the Relaxation package. This function is simple to use. Read Excel file path. Sheet equals sheet 1 loads the data from the specified sheet. To install the package, you must run install packages Relaxation once. The Relaxation package is great because it handles multiple sheets and preserves cell formatting such as dates and numbers without requiring external dependencies. This makes it ideal for working with complex Excel files. Writing data to Excel files in R is done using the write XLSX function from the XLSX package. The syntax is write XLSX data, output XLSX, sheet equals sheet 1. Before using this function, you need to install the XLSX package with install packages XLSX. However, be aware that this package requires a Java runtime environment to function. This dependency can sometimes cause issues, so it's worth noting if you encounter errors. Once set up, right, XLSX allows you to save your data to Excel files, making it easy to share results with colleagues who may prefer working in Excel. CSV files are not always comma-separated. Some files use different delimiters like semicolons, tabs, or even custom characters. In such cases, the seep parameter in read CSV or the readdLM function from the reader package becomes essential. For example, read CSV data txt seep equals tells R to use semicolons as separators. The reader readdLM function offers even more flexibility, allowing you to define custom delimiters and handle complex file structures. This is particularly useful when working with international data or files generated by other software. When importing data, you may encounter missing values, which are often represented as empty cells or specific markers like na. The nastrings parameter in read CSV lets you define what constitutes a missing value. For example, read CSV data CSV nastrings equals C. Na ensures that both empty cells and the string na are treated as missing. After importing, you can clean the data using functions like naomit to remove rows with missing values, or titter. Replace na to fill them with a specified value. Handling missing data is a critical step in ensuring the accuracy of your analysis. Several issues can arise when importing data. One common problem is file path errors, which occur when R cannot locate the file. To check your current working directory, use the getHood function. Encoding issues, such as non-ASCII characters, can be resolved by specifying the filing coding parameter. For example, read CSV data, CSV, filing coding equals UTF-8 ensures proper handling of special characters. Data type mismatches, where columns are read as characters instead of numbers, can be addressed with the call class's argument. For instance, read CSV data, CSV, call classes equals C character. Numeric explicitly defines column types, preventing errors during analysis. After importing data, it's crucial to clean and prepare it for analysis. Start by examining the data structure using SDR data or head data to check for unexpected values or formatting issues. Remove duplicates with distinct from the deepler package, which ensures each row is unique. Inconsistent formatting, such as dates in different formats or categories with typos, can be addressed using functions like titter, separate to split columns, or titter, unite to combine them. These steps ensure your data is consistent and ready for further processing. In summary, CSV and Excel files are widely used for storing and sharing data, and R provides robust tools to work with them. Functions like read CSV, read Excel, and write XLSX make it easy to import and export data, while additional parameters and packages allow for flexibility in handling different formats and issues. Practicing these techniques will help you efficiently work with real-world datasets. In the next session, we will dive into data manipulation using the deepler package, which will build on the skills you've learned here. Keep experimenting with these functions to solidify your understanding. Data export plays a crucial role in the workflow of any data scientist or analyst. When you share your findings with colleagues, save your progress for future reference, or integrate your data with other software tools, the ability to export data becomes essential. R, being a powerful statistical programming language, offers a variety of built-in functions to handle this process seamlessly. These functions allow you to transform your data into formats that can be easily accessed and manipulated by others or different applications. Understanding these export methods is not just about technical proficiency. It's about ensuring that your work is reproducible, transparent, and collaborative. Whether you're working on a research project, a business report, or a machine learning model, the way you export your data can significantly significantly impact how others interact with your results. When it comes to data export, choosing the right file format is key. Let's explore the most common options. CSV files, or comma-separated values, are a simple and widely supported format. They are ideal for spreadsheets and basic data sharing because they are plain text and can be opened in programs like Excel, Google Sheets, or even a basic text editor. Excel files, on the other hand, offer more flexibility. They can contain multiple sheets, support advanced formatting, and are perfect for detailed reports or data with complex structures. JSON, which stands for JavaScript Object Notation, is a lightweight format often used in web applications. It's excellent for structured data that needs to be transferred between a server and a web application. Finally, RData files, such as RDA or RData, are specifically designed to preserve R objects. These files are invaluable when you want to save your entire workspace or specific objects for later use in R without losing any metadata or structure. Exporting data to a CSV file is one of the most straightforward tasks in R. The right CSV function is your go-to tool for this. It takes a data frame and writes it to a file, separating each value with a comma. For example, write CSV data. File name CSV will save your data into a file named filename CSV. However, if you're working in a region where commas are used as decimal separators, you might want to use write CSV2 instead. This function replaces commas with semicolons, which is standard in many European countries. It's important to note that CSV files are plain text, so they don't support complex data types like dates or formulas. Always ensure your data is clean and properly formatted before exporting, as any inconsistencies can lead to errors when others open the file. Exporting to Excel files requires a bit more setup, since R's base installation doesn't include this functionality. You'll need to install and load a package like XLSX or OpenSUSE. Once installed, the right XLSX function becomes your ally. For instance, write XLSX data, file name XLSX, will save your data into an Excel file. This method is particularly useful if you need to maintain formatting, such as cell colors, fonts, or multiple sheets. Excel files can also contain multiple sheets, allowing you to organize different parts of your data in separate tabs. This is especially helpful when presenting results to stakeholders who may need to navigate through various datasets. However, be cautious with large data sets, as Excel has limitations on the number of rows and columns it can handle. If you're working with web applications or APIs, JSON files are an excellent choice. The JSONlite write-in function in R allows you to export data frames into JSON format, which is easy to parse and use in web environments. For example, JSONlite write-in data. File name JSON will generate a JSON file. JSON is particularly useful for structured data, such as hierarchical or nested information, making it a favorite among developers. It's also language independent, meaning it can be read by almost any programming language, which enhances its versatility. When sharing data with a web developer or integrating your results into a web-based tool, JSON provides a reliable and efficient solution. Just remember to validate your JSON files to ensure they're correctly formatted and free of syntax errors. Sometimes you'll need to save R objects themselves rather than just data. The save function is perfect for this. By using save data, file equals data, RData, you can store your entire object in a file that can be loaded back into R later. This is ideal for preserving complex data structures, models, or any R objects you've created. If you want to share the code to recreate an object instead of the object itself, dput data, data R is the way to go. This function writes the object's definition as R code, which can be sourced later to recreate the object. This is particularly useful for debugging or sharing reproducible code snippets. Whether you're saving for future use or collaborating with others, these methods ensure your R objects are preserved accurately. To ensure your data exports are effective and error-free, follow these best practices. First, always verify that your data is clean and properly formatted. Missing values, incorrect data types, or inconsistent structures can cause issues when others use the file. Second, adopt consistent naming conventions for your files. Using descriptive names with dates or version numbers can save you time and confusion later. Third, document the export process thoroughly. This includes noting the date, the function used, and any specific parameters. Finally, test your exported files in the target applications. Open the CSV in a spreadsheet. Check the Excel file for formatting, or validate the JSON file with an online tool. These steps not only prevent errors, but also make your work more transparent and reproducible. In conclusion, data export is a fundamental skill for anyone working with R. It ensures that your results are accessible, reusable, and compatible with various tools and platforms. Choosing the right format depends on your specific needs, whether it's simplicity, advanced formatting, or integration with web applications. R provides a wide range of tools to handle these tasks efficiently. However, the true value of these tools lies in how you use them. Always take the time to validate your exported files, follow best practices, and consider the end user's perspective. By doing so, you not only enhance your own workflow, but also make your work more collaborative and impactful. Remember, the goal of data export is not just to save data, but to share knowledge effectively. Good morning, everyone. Today, we'll explore Deepler, a powerful R package designed to make data manipulation more straightforward and efficient. As part of the Tidyverse, which is a collection of R packages aimed at streamlining data science workflows, Deepler focuses on simplifying the often complex task of data wrangling. Whether you're filtering rows, selecting columns, or summarizing data, Deepler provides a consistent and intuitive set of functions that make these operations easier to understand and implement. Its design emphasizes clarity, allowing you to focus more on the insights you want to extract from your data rather than the mechanics of the code. The core of Deepler lies in its 5 key functions, which are essential for most data manipulation tasks. The filter function allows you to subset rows based on specific conditions, such as selecting only entries where a variable exceeds a certain value. The select function helps you choose which columns to retain or exclude from your dataset. The mutate function is used to add new variables or modify existing ones, making it ideal for creating derived metrics. The arrange function sorts your data by one or more variables, while the summarize function computes summary statistics. Together, these functions form the foundation for a wide range of data analysis tasks. Let's dive deeper into the filter function. This tool is incredibly useful for narrowing down your data to specific subsets. For example, if you have a data set of people and you want to find those older than 30, you would use filter data age 30. You can combine multiple conditions using logical operators like and or. For instance, filter data age 30 and gender equals female would select individuals who are both older than 30 and female. Additionally, handling missing values is straightforward with functions like ISNA to identify missing data or ISNA to exclude it. This ensures your analyses are not skewed by incomplete information. Next, the select function is designed to help you manage the columns in your dataset. If you only need specific variables, such as name and score, you can use select data, name, score. This is particularly useful when working with large datasets where many columns are irrelevant to your analysis. Deepler also offers helpful functions like starts with, ends with, and contains to select columns based on patterns in their names. For example, select data starts with math would retrieve all columns beginning with math. Additionally, the rename function allows you to modify column names for clarity, making your data easier to interpret. The mutate function enables you to create new variables or transform existing ones. For instance, if you have math and science scores, you could calculate a total by using mutate data. Total equals math plus science. This is especially useful for generating new metrics that are not already present in your dataset. When dealing with conditional transformations, functions like Eiffels and casewin come in handy. For example, mutate data, category equals Eiffels score 90. High, low would assign a category based on a threshold. Another variant, transmute, is similar to mutate, but drops all original columns except the ones you create, which is ideal for simplifying datasets. Sorting your data is a common task, and the arrange function makes it simple. To sort by a single variable, you might use a redact score. If you want to sort in descending order, you can wrap the variable in desc, as in a redact disk score. For multiple variables, you can list them in the function, such as a redact category score. This is often used after filtering or summarizing to present data in a more meaningful order. For example, after filtering for high-performing students, you might sort them by their scores to see the top performers. The summarize function is essential for generating summary statistics, such as averages, totals, or counts. For example, summarize data, avg score equals mean score would calculate the average score across all rows. When combined with group B, you can compute metrics for different groups within your data. If you have a data set of sales by region, you could use group data, region followed by summarize of sales equals mean sales to get the average sales per region. Common functions like mean, sum, min, max, and n are frequently used to extract key insights from your data. Grouping data is a powerful way to analyze subsets of your dataset independently. The Group B function allows you to specify one or more variables to group by, such as group by data category. Once grouped, any subsequent operations like summarize or mutate will be applied within each group. For instance, if you group by gender, you can calculate summary statistics for males and females separately. It's important to remember that after you're done with grouped operations, you should use ungroup to reset the grouping, ensuring that future functions operate on the entire dataset. One of the most valuable features of Deepler is its ability to chain functions together using the pipe operator %%. This operator allows you to write code that reads like a sequence of steps, making it easier to follow. For example, data %% filterage 30% summarize of income equals mean income would first filter the data and then compute the average income. This approach is not only more readable, but also helps prevent errors by breaking down complex tasks into manageable parts. By combining mutate, filter, and summarize, you can tackle intricate data problems with clarity and efficiency. Let's apply these concepts to a real-world example using the MT-Cars dataset. First, we might load the data and filter for cars with a miles per gallon rating higher than 20. Then, we could select specific columns like cylinders, horsepower, and weight. Next, we might use mutate to create a new variable, such as mpg/perp, which is the ratio of miles per gallon to horsepower. Finally, we could group the data by the number of cylinders and summarize the average miles per gallon for each group. This step-by-step process demonstrates how Deepler's functions work together to extract meaningful insights from a dataset. To get the most out of Deepler, it's important to follow some best practices. First, always use the pipe operator %% to make your code more readable and maintainable. Avoid relying on base R functions unless necessary, as Deepler's syntax is often more intuitive. Document your code with comments to explain complex steps, which is especially helpful for collaboration. Finally, test each step individually before chaining them together. This ensures that any issues are identified early, saving time and effort in debugging. In summary, Deepler is a game changer for data manipulation in R, offering a consistent and user-friendly set of tools. Mastering the 5 key functions: filter, select, mutate, arrange, and summarize will significantly enhance your ability to work with data efficiently. By combining these functions with the pipe operator, you can create powerful, readable workflows that simplify even the most complex tasks. Remember to practice with real data sets to build confidence and uncover deeper insights. With Deepler, the possibilities for data analysis are vast and rewarding. Good morning, everyone. Today we will explore Titter, a powerful package within the Tidyverse ecosystem designed for data transformation. Titter's primary goal is to reshape and clean data so it adheres to the principles of tidy data. Tidy data is structured in a way that each variable forms a column, each observation forms a row, and each value is a single cell. This structure makes data easier to analyze and visualize. The key functions in Titter include gather, spread, separate, and unite. These functions allow us to convert data between wide and long formats, split columns into multiple parts, and combine columns into one. Titter works seamlessly with Deepler, another core Tidyverse package, enabling efficient data manipulation workflows. Together, these tools form the backbone of data preparation in R. To begin using Titter, we first need to install it. The installation command is install packages.titter. Once installed, we load the package using the library function, specifically library Titter. However, Titter is part of the larger Tidyverse collection of packages. Therefore, it is recommended to install the entire Tidyverse suite with install packages.tidyverse. This ensures that all related packages, including Titter and Deepler, are available for use. By installing Tidyverse, we streamline the process of accessing multiple tools, making our data analysis tasks more efficient. Now, let's delve into the key functions of Titter. The gather function is used to transform wide data into long format. This means converting columns into rows, which is particularly useful when dealing with datasets where each row represents multiple measurements. The spread function does the opposite, converting long data back into wide format by turning rows into columns. The separate function allows us to split a single column into multiple columns based on a delimiter, such as a space or a comma. Finally, the unite function combines multiple columns into one, often using a separator like a space or an underscore. These functions are essential for reshaping and cleaning data to meet the tidy data standards. Let's take a closer look at the gather function. The syntax for gather is gather data, key, value, ... Here, data refers to the input data frame. Key is the name of the new column that will hold the original column names, and value is the name of the column that will hold the original values. The ... allows us to specify which columns to gather. For example, if we have a data frame with columns like age and score, we can use gather to convert these into rows. An example command might be gather df, key equals variable, value equals value, minus id this would gather all columns except id into the variable and value columns. This transformation is invaluable for preparing data for analysis or visualization. The spread function complements gather by converting long data back into wide format. Its syntax is spread data, key value. Here, data is the input data frame. Key is the column containing the new column names, and value is the column containing the values. For instance, if we have a data set where each row represents a variable and its value, spread can reorganize it into columns. An example command would be spread df, key equals variable, value equals value. This function is particularly useful when we need to pivot data for reporting or further analysis. It's important to note that spread assumes unique keys. If duplicates exist, additional parameters like fill or na-rem can be used to handle them. The separate function is designed to split a single column into multiple columns. Its syntax is separate data, call into seep. Here, data is the input data frame. Call is the column to split. Into is a vector of new column names, and seep is the delimiter used to split the column. For example, if we have a column named name containing first and last names separated by a space, we can split it into first and last columns. The command would be separate df, call equals name, into equals c first last, seep equals space. This function is essential for parsing complex data, such as dates or addresses, into their constituent parts. The unite function is the inverse of separate, combining multiple columns into a single column. Its syntax is unite data, call ... seep equals underscore. Here, data is the input data frame. Call is the name of the new column. ... specifies the columns to combine, and seep defines the separator. For example, if we have first and last name columns, we can unite them into a full name column using a space as the separator. The command would be unite df. Call equals full name, first, last, sep equals space. This function is useful for creating composite identifiers or simplifying data structures for specific use cases. Let's explore practical examples of titter in action. First, consider reshaping survey data from wide to long format. If a dataset has columns for each response category, Gather can convert these into rows, making it easier to analyze trends. Second, splitting a date column into year and month. If the date is stored as a string like 2020-304, Separate can split it into year and month columns. Third, combining first and last names into a single column. Using Unite, we can merge these into a full name, which is often required for reports or user interfaces. These examples illustrate how Titter simplifies data transformation tasks, making it a vital tool in the data analyst's toolkit. When working with Titter, there are common issues to be aware of. One such issue is duplicated keys when using spread. This occurs when multiple rows have the same key value pair, leading to errors. To resolve this, we can use the fill parameter to specify a default value, or the na-rem parameter to remove missing values. Missing values can also cause problems, so it's important to handle them using na-rem or the fill function. Additionally, ensuring consistent column names is crucial. Mismatches in naming can lead to unexpected results, so always validate your data before applying transformations. These practices help maintain data integrity and avoid errors during analysis. To get the most out of Titter, follow these best practices. First, maintain tidy data throughout your workflow, as this simplifies analysis and visualization. Second, pair Titter with Deepler for a streamlined data manipulation process. Deepler's functions for filtering, summarizing, and arranging data complement Titter's reshaping capabilities. Third, always validate your data after transformations to catch any inconsistencies. Finally, document each step of your process to ensure reproducibility. This is especially important when working in teams or revisiting projects later. By adhering to these practices, you can maximize the efficiency and reliability of your data analysis. In conclusion, Titter is an indispensable tool for reshaping and cleaning data in its functions like gather, spread, separate, efficient data transformation, while integration with deeper enhances overall workflow. By mastering these tools, you can tackle complex data challenges with confidence. Remember to handle common issues like duplicated keys and missing values, and always prioritize tidy data principles. As you continue exploring R, Titter will become a valuable asset in your data analysis journey. Thank you for your attention, and feel free to ask questions or share your experiences with these functions. Aggregation and summarization are fundamental techniques in data analysis that allow us to condense large data sets into meaningful insights. Aggregation involves combining data points into summary statistics, such as averages, totals, or counts, while summarization focuses on extracting the most relevant information from these data sets. These processes are essential for making sense of complex data, enabling clearer communication of findings and supporting informed decision-making. In fields like finance, where tracking trends in stock prices or revenue is critical, in research for analyzing experimental results, and in business intelligence for monitoring key performance indicators. These methods form the backbone of data-driven strategies. By mastering aggregation and summarization, analysts can transform raw data into actionable knowledge. R provides a variety of functions for aggregation and summarization, each with its own strengths. The base R function aggregate is a straightforward tool for applying functions to subsets of data. For more flexible and readable workflows, the Deepler package offers groupby and summarize, which streamline operations through a consistent syntax. The data table package is particularly powerful for handling large data sets efficiently, leveraging optimized performance. Additionally, the Tapley function is useful for applying functions to subsets of data defined by factors. Choosing the right tool depends on the complexity of the task, the size of the data, and the desired level of readability. These functions collectively empower users to tackle a wide range of aggregation challenges. The aggregate function in R is a foundational tool for basic aggregation tasks. Its syntax is structured as aggregate formula data fun, where the formula defines the relationship between variables. The data argument specifies the dataset, and fun is the function to apply. For example, using aggregate SIL, data equals empty cars, mean calculates the average miles per gallon for each cylinder category in the MTCARS dataset. This function can handle multiple variables and apply various functions simultaneously, making it versatile for simple tasks. However, it is limited to base R and may feel less intuitive for users accustomed to more modern approaches. Despite this, it remains a reliable option for quick analyses and foundational understanding. The deepler approach to aggregation leverages the power of the Tidyverse, offering a clean and intuitive workflow. By chaining Group B and Summarize, users can perform complex operations with minimal code. For instance, MTCARS %% group bacil %% summarize equals mean count equals n groups the data by cylinder count and calculates the average miles per gallon alongside the number of observations in each group. This method enhances readability and aligns with modern R practices, making it easier to follow and modify. Furthermore, Deepler integrates seamlessly with other Tidyverse tools like ggplot2 for visualization, creating a cohesive ecosystem for data analysis. This approach is particularly beneficial for users who prioritize clarity and maintainability in their code. Common aggregation operations in R include calculating the mean for averages, sum for totals, n for counts, and min and max for extremes. Additionally, functions like SD and var measure variability in the data. These operations are essential for understanding central tendencies, distribution patterns, and overall dataset behavior. For example, the mean provides a typical value, while the standard deviation reveals how spread out the data points are. Using these functions together allows analysts to create comprehensive summaries that highlight key aspects of the data. Mastery of these operations enables users to address diverse analytical questions effectively, from simple descriptive statistics to more nuanced exploratory analyses. Handling missing data is a critical aspect of aggregation, as incomplete datasets can lead to biased or misleading results. Most R functions include an NARM argument to remove missing values during computation. For instance, mean data. NARM equals true calculates the average while ignoring any nut entries. Preprocessing steps like complete cases or no omit can also be used to filter out rows with missing values before analysis. However, it is important to consider the impact of missing data on the results and document any adjustments made. Techniques such as imputation, where missing values are estimated based on other data, may be necessary in some cases. Addressing missing data thoughtfully ensures that summaries are accurate and representative of the underlying information. Adhering to best practices in aggregation and summarization ensures reliable and reproducible results. Using Deepler is recommended for its clarity and efficiency, as its syntax is both readable and consistent. Documenting the logic behind each step, such as specifying the function used and any data transformations, enhances reproducibility. Visualizing aggregated data with tools like ggplot2 can provide additional insights and help validate findings. It is also important to avoid over-reliance on single summary statistics, as they may not capture the full picture. Instead, combining multiple metrics offers a more comprehensive understanding. By following these practices, analysts can produce robust, transparent, and impactful data summaries. Aggregation and summarization are indispensable skills for any data analyst, enabling the transformation of raw data into meaningful insights. As you continue to practice, explore real-world datasets to apply these techniques in diverse contexts. Whether analyzing financial trends, scientific experiments, or business metrics, these methods will serve as a foundation for effective data-driven decision-making. Remember to stay curious, experiment with different functions, and seek feedback to refine your approach. By mastering these techniques, you will be well equipped to tackle complex analytical challenges and contribute valuable knowledge to your field. Good morning, everyone. Today, we'll explore the essential techniques for merging and combining datasets in R when working with data. It's rare to have all the information you need in a single table. Merging and concatenation allow us to bring together disparate datasets to create a more complete picture. For example, imagine you have customer information in one dataset and their purchase history in another. Combining these datasets enables deeper analysis, such as identifying which customers are the most valuable. These methods are crucial in fields like business intelligence, scientific research, and data science. Common scenarios include merging tables based on shared keys, appending rows to add more observations, or combining columns to expand the features available for analysis. Understanding these concepts is the first step in mastering data integration. let's dive into the different types of joins available in R. An inner join is like finding the intersection of two datasets, retaining only the rows where there is a match in the key columns. A left join keeps all the rows from the first dataset, known as the left table, and adds matching rows from the second dataset, the right table. This is useful when you want to ensure no data from the left table is lost. Similarly, a right join does the opposite, preserving all rows from the right table. A full join combines all rows from both datasets, filling in missing values where there is no match, which is ideal for scenarios where you need to see all possible data. Lastly, an anti-join helps identify rows in one dataset that do not have corresponding entries in the other, which can be useful for detecting outliers or unique entries. Each join type serves a specific purpose, and choosing the right one depends on your analysis goals. Now, let's discuss how to perform these joins using the Deepler package. Deepler provides intuitive functions like inner join, left join, right join, full join, and anti-join. These functions require a common key column between the datasets, such as an ID or a name. For example, using left join1 df2 by equals key column merges df2 into df1 based on the key column. One of the strengths of Deepler is its seamless integration with the tidyverse, making it easier to chain operations and handle large datasets efficiently. Unlike base R functions, Deepler's syntax is consistent and readable, reducing the likelihood of errors. Whether you're working with small datasets or big data, Deepler's performance optimizations ensure your code runs smoothly. Remember to always check that your key columns are correctly specified to avoid unexpected results. In addition to joins, we often need to combine datasets by rows or columns. The rbind function stacks datasets vertically, but it requires that the datasets have the same columns in the same order. For instance, if you have two datasets with identical variables like age and income, rbind can merge them into a single dataset. On the other hand, cbind combines datasets horizontally, adding columns to the right of the existing data. However, cbind requires that both datasets have the same number of rows. To handle these scenarios more flexibly, the bindrows and bindcalls functions from Deepler are highly recommended. These functions can handle datasets with slightly different structures, automatically filling missing values with na where necessary. For example, bindroust1 df2 will stack rows from df1 even if their columns differ slightly. Mastering these tools allows you to efficiently merge data in various formats. Before performing any joins or combinations, there are several key considerations to keep in mind. First, ensure that column names and data types are consistent across datasets. Mismatched names or types can lead to errors or incorrect results. For example, a numeric column named A and a character column named A may not be recognized as the same. Second, handle duplicates and missing values appropriately. If a key column has duplicates, the join may produce more rows than expected, so it's important to clean your data beforehand. Base R offers the merge function as an alternative to Deepler's joins, but Deepler is generally more user-friendly. Finally, always validate your merged dataset by checking for inconsistencies, such as unexpected null values or duplicate rows. This step ensures the integrity of your data before proceeding with analysis. Despite their usefulness, joins and combinations can lead to common pitfalls. One frequent issue is mismatched key columns, such as using a different name or data type in the key. For example, if one dataset uses ID and another uses ID, the join may fail silently. Another trap is ignoring case sensitivity or data type mismatches, which can cause unexpected results. When working with large datasets, performance can also become a concern, as some joins may take significant time or memory. To avoid this, consider optimizing your data structures or using efficient functions. Lastly, forgetting to specify the correct by parameter in join functions can lead to incorrect merges. Always double-check your key columns and test your code with smaller datasets before applying it to the full data. To recap, joining and combining datasets is a foundational skill in data analysis. Tools like Deepler make these tasks intuitive and efficient, allowing you to focus on insights rather than data preparation. Practice is key. Experiment with real-world datasets to see how these techniques apply in different contexts. Whether you're merging customer data or appending experimental results, the principles remain the same. Always take the time to validate your merged data, ensuring accuracy and consistency. By mastering these techniques, you'll be better equipped to tackle complex data challenges and derive meaningful conclusions from your work. Thank you, and I look forward to your questions. Data cleaning is a foundational step in any data analysis project. as it ensures the accuracy and reliability of your findings. Without proper cleaning, even the most sophisticated models can produce misleading results. Common issues that arise in datasets include missing values, which are often represented as na in R, duplicates that can skew statistics, and inconsistent formatting, such as varying date formats or misspelled categories. Fortunately, R offers a robust set of tools to tackle these challenges. From functions like ISNA to packages like titter, R provides the flexibility to identify and resolve these issues efficiently. Understanding these tools is essential for any data scientist or analyst working with real-world data. To begin the data cleaning process, identifying missing values is crucial. In R, the ISNA function allows you to detect these missing entries across your dataset. For example, if you have a data frame called DF, running is NADV will return a logical matrix indicating which elements are missing. Additionally, the summary function provides a quick overview of the number of missing values per column, which is especially useful for large datasets. Another helpful function is complete cases, which returns a logical vector indicating which rows contain no missing values. This can be used to filter your data, ensuring that only complete cases are analyzed. These tools form the first line of defense in addressing data quality issues. When dealing with missing data, it's important to understand the underlying mechanism that caused the missingness. There are three primary types of missing data: MCAR, MAR, and MNAR. MCAR stands for missing completely at random, meaning the missing values have no relationship to any other variables in the dataset. For example, if a sensor randomly fails, the resulting missing data would be MCAR. MAR, or missing at random, occurs when the missingness is related to other observed variables. For instance, if younger individuals are less likely to report their income, the missing income data is MAR. Finally, MNAR, or missing not at random, happens when the missingness is related to unobserved variables. An example might be that people with lower incomes are more likely to refuse to answer income questions, making the missingness dependent on an unmeasured factor. Recognizing the type of missingness helps determine the most appropriate strategy for handling it. Once missing values are identified, the next step is to decide how to handle them. A common approach is to remove the affected rows or columns using functions like no-omit, which filters out any rows containing missing values. However, this method can lead to a loss of valuable data, especially if the missingness is widespread. Another approach is imputation, where missing values are replaced with estimated values. For numerical data, this might involve using the mean or median of the column, while for categorical data, the mode is often used. Advanced techniques, such as model-based imputation, leverage algorithms to predict missing values based on relationships within the dataset. Packages like mice in R provide tools for multiple imputation, which accounts for the uncertainty in the imputed values. Choosing the right strategy depends on the nature of the data and the context of the missingness. Two functions that are particularly useful for handling missing values are no-omit and null. The no-omit function removes any rows that contain missing values, making it a straightforward way to ensure your dataset is complete. However, it's important to note that this approach can reduce the sample size and potentially introduce bias if the missingness is not random. On the other hand, null does not remove any data, but instead throws an error if any missing values are present. This is useful for data validation, ensuring that your analysis only proceeds when the dataset is clean. Both functions play a role in maintaining data integrity, but their use depends on the specific requirements of your project. Imputation techniques offer a way to preserve the dataset's size while addressing missing values. For numerical variables, mean or median imputation is often used. For example, replacing missing values in a column with the mean of that column can be done using code like dfis, nadv, meanv, narm equals true. However, this method can underestimate variability and may not capture complex patterns in the data. For categorical variables, mode imputation is more appropriate, where the most frequent category is used to fill in missing values. While these methods are simple and quick, they can introduce bias if the missingness is not random. It's important to evaluate the impact of imputation on your analysis and consider more advanced techniques when necessary. For more sophisticated handling of missing data, the mice package in R provides a powerful solution through multiple imputation. This technique involves creating multiple complete datasets by filling in missing values with plausible estimates, then combining the results of analyses performed on each dataset. The process begins by installing and loading the mice package, followed by using the mice function to generate imputed datasets. Once imputed, you can analyze each dataset using the with function and pool the results using the pool function. This approach accounts for the uncertainty in the imputed values, leading to more reliable statistical inferences. Multiple imputation is particularly useful when missingness is not completely random, and when preserving the dataset's structure is critical. To illustrate these concepts, let's consider a real-world dataset like air quality, which contains measurements of air pollution in New York. This dataset has missing values in the ozone column, represented as Na. Using the ISNA function, we can identify these missing entries and assess their distribution. Depending on the context, we might choose to remove the affected rows with no omit, impute the missing values using the mean or median, or apply a more advanced method like multiple imputation. The choice of technique should be guided by the nature of the missingness and the goals of the analysis. By applying these methods, we can ensure that our dataset is ready for further exploration and modeling. Adopting best practices in data cleaning helps ensure the quality and reproducibility of your work. First, always document the steps you take to handle missing values, as this provides transparency for others reviewing your analysis. After cleaning, validate your data by checking summary statistics or visualizing patterns using tools like ggplot2. Visualizations can reveal trends or anomalies that might not be apparent from numerical summaries alone. Additionally, consider the implications of your cleaning decisions on the final results. For example, removing too many rows might reduce the statistical power of your analysis, while imputation could introduce bias if not done carefully. By following these practices, you can build more trustworthy and robust models. In conclusion, data cleaning is a critical step in the analysis process, and addressing missing values is a key component of this task. Whether you choose to remove, impute, or model missing data, the approach should be guided by the specific characteristics of your dataset and the goals of your analysis. R provides a wide range of tools, from basic functions like ISNA to advanced packages like mice, to help you tackle these challenges. Mastering these tools not only improves the quality of your data, but also enhances the reliability of your insights. As As you continue to work with real-world datasets, remember that thoughtful and systematic data cleaning is the foundation of any successful analysis. Good morning. Today, we will explore the fundamentals of base R graphs, which are essential tools for visualizing data directly within the R programming language. Base R provides a suite of built-in functions that allow users to create a variety of visualizations without the need for additional packages. This makes it an accessible starting point for anyone learning data analysis. These functions are designed to be intuitive, automatically detecting data types such as numeric or categorical variables. Common graph types include scatter plots, histograms, bar charts, and box plots, each serving a unique purpose in data exploration. Whether you are analyzing trends, distributions, or comparisons, mastering these basic graphics will lay a strong foundation for more advanced statistical work. Let's begin by examining the most versatile function in base R, the plot function. The plot function is the cornerstone of data visualization in R. It is incredibly flexible, capable of generating scatter plots, line graphs, and even histograms, depending on the input data. The basic syntax is plot x, y, where x and y represent the variables you wish to plot. For data frames, simply passing the data to plot will generate a scatter plot of all numeric variables against each other. One of the most useful features of plot is its ability to automatically detect data types. For example, if you pass a single numeric vector, it will create a line graph, while two vectors will produce a scatter plot. Let's take a practical example. Plotting miles per gallon against horsepower from the MT cars dataset. This simple command, plot cars $mpg, MT cars $HP, will instantly reveal any potential relationships between these two variables. Understanding how to use plot effectively is crucial, as it forms the basis for many other graphical functions in R. Next, we turn to bar charts, which are ideal for visualizing categorical data. The bar plot function in R allows you to create bar charts by specifying the heights of the bars and their corresponding labels. The syntax is straightforward. Barplathite names arg, where height represents the values to be plotted, and names arg provides the labels for each category. Instance, using the MT cars dataset, we can count the frequency of different cylinder counts with table cars $sil, and then pass this to bar plot. This will generate a bar chart showing how many cars have 4, 6, or 8 cylinders. Customization options such as colors, labels, and orientations make it easy to tailor the chart to your needs. For example, you can adjust the x-axis and y-axis labels to provide clear context, or rotate the bars for better readability. Bar charts are particularly useful when comparing the frequency or magnitude of different categories. Histograms are another fundamental tool for visualizing the distribution of numeric data. The hist function in R creates a histogram by dividing the data into bins and displaying the frequency of each bin. The syntax is histex, breaks call, where x is the numeric vector. Breaks determines the number of bins, and call sets the color of the bars. For example, Histamcar's $MPG call equals light blue, main equals MPG distribution will generate a histogram of the miles per gallon values with light blue bars and a descriptive title. Adjusting the brakes parameter allows you to control the granularity of the visualization, which can be critical for identifying patterns or outliers. Histograms are especially valuable for understanding the shape of a dataset's distribution, whether it is normal, skewed, or multimodal. By experimenting with different bin sizes, you can gain deeper insights into the underlying data. Box plots, created using the boxplot function, provide a concise summary of a dataset's distribution. They display key statistics such as the median, quartiles, and potential outliers. The syntax is boxplotex, where x can be a numeric vector or a formula specifying the relationship between variables. For example, Boxplimtcar's $MPG, MTcar's $SIL, xlab equals cylinders, ilab equals MPG will generate a box plot comparing the miles per gallon values across different cylinder counts. This visualization is particularly useful for identifying differences in spread and central tendency between groups. The box plot's ability to highlight outliers makes it a powerful tool for detecting anomalies in the data. By using this function, you can quickly compare distributions and make informed decisions based on the underlying structure of your dataset. Scatter plots and line graphs are essential for exploring relationships between variables. Scatter plots, created using the plot function, display individual data points to reveal patterns or correlations. Line graphs, on the other hand, Use the type equals L parameter to connect data points in a sequence, making them ideal for time series or continuous data. For example, plotcars $WT, MTcars $MPG, PCH equals 19. Call equals red will generate a scatter plot of car weight versus miles per gallon, with red solid circles as markers. Adding labels, titles, and legends enhances the clarity of the graph. The XLab and ILLab parameters set axis labels, while the main parameter adds a title. Legends are particularly useful when multiple datasets are plotted on the same graph, helping to distinguish between different series. These visualizations are critical for identifying trends, clusters, or potential outliers in your data. Customization is key to creating clear and effective visualizations. R provides a range of parameters to modify the appearance of your graphs. The call parameter controls the color of points or bars. PCH adjusts the shape of points. LWD changes the line width, and SEX scales the size of text or symbols. For instance, plot, call equals blue, PCH equals 17, LWD equals 2 will produce a graph with blue triangles and thicker lines. These adjustments allow you to emphasize specific aspects of your data or align the visuals with your presentation style. Additionally, adding titles and axis labels with main, XLab, and ILLab ensures that your audience understands the context of the graph. The legend function further enhances readability by explaining different data series. By mastering these customization options, you can transform basic plots into polished, informative graphics. Once you have created a graph, it's important to save it for future use or sharing. R offers several functions for this purpose, including PNG, PDF, and JPEG. The process involves opening a graphics device, generating the plot, and then closing the device. For example, using PNG file name PNG plot, dev off will save the current plot as a PNG file. It's crucial to specify the correct file path and format to ensure compatibility. Always remember to call dev off after saving, as this finalizes the file and releases system resources. Different formats suit different needs. PNG is ideal for web use, PDF for high-quality print, and JPEG for compressed images. By learning how to save your graphs, you can easily integrate them into reports, presentations, or other projects. In conclusion, base R graphs are a powerful and versatile set of tools for data visualization. By mastering functions like plot, bar plot, hist, and box plot, you gain the ability to explore and communicate insights from your data effectively. Customization options allow you to refine these visualizations to suit your specific needs, while saving plots ensures they can be shared or reused. Practice is essential to becoming proficient, so take the time to experiment with different datasets and parameters. As you build your skills, you'll find that these foundational techniques are invaluable for both exploratory analysis and presenting results. Keep refining your approach, and you'll be well equipped to tackle more advanced graphical tools in our Thank you for your attention. And I hope you find these techniques useful in your own work. Good morning, everyone. Today, we'll dive into the world of advanced visualizations using the R programming language, specifically focusing on the ggplot2 package. ggplot2 is a powerful tool that allows us to create complex and aesthetically pleasing data visualizations. It's built on the grammar of graphics, which means it breaks down plots into logical components, making it easier to build and modify them. Advanced plots are essential in data analysis because they help us uncover patterns, trends, and outliers that might not be obvious in raw data. They also play a crucial role in storytelling, enabling us to present findings in a clear and compelling way. By the end of this session, you'll have a solid understanding of key objectives like layering, faceting, customization, and best practices. Let's get started. Now, let's explore how to construct layered plots in ggplot2. The grammar of graphics is the foundation of this package, and it consists of three main elements: the ggplot function, geometric objects geomes like geome point or geome line, and aesthetic mappings, eyes that define how data variables are mapped to visual properties. To build a plot, you start with ggplot, which sets up the data and aesthetic mappings. Then you add layers using the plus operator to incrementally build your visualization. For example, you might start with a scatter plot of points, then overlay a line to show trends, or add bars to compare categories. This layering approach gives you full control over your plot's composition. Remember, each layer can have its own data, mappings, or parameters, making it incredibly flexible for complex visualizations. Next, we'll discuss faceting, a technique that splits your data into subplots to compare different subsets. The two main functions for faceting are face trap and face grid. face trap is ideal for one-dimensional splits, such as creating separate plots for each category in a single variable. Phased grid, on the other hand, allows for two-dimensional splits, like dividing data by two variables. For instance, if you're analyzing sales data across regions and product types, faceting can help you visualize each combination in its own subplot. Customizing facet labels and spacing is also important to ensure clarity. You can adjust the appearance of axis labels, add titles, or modify the spacing between subplots to make the overall plot more readable. This technique is particularly useful when dealing with categorical variables that have many levels. Moving on to advanced geomes and aesthetics, ggplot 2 offers a variety of geometric objects beyond the basic ones like points and bars. For example, geome density D creates contour plots to show the density of points in 2 dimensions, which is useful for identifying clusters or patterns. Geome jitter adds random noise to points to avoid overplotting, while geome spoke draws lines from a central point to indicate direction or magnitude. When mapping aesthetics, you can use color, size, shape, and transparency alpha to encode additional variables. For instance, you might use color to differentiate categories, size to represent a numerical value, and alpha to show the density of overlapping points. Combining these geomes and aesthetics allows you to create multi-dimensional insights, making your plots more informative and engaging. Customizing themes and styles is essential for creating professional-looking visualizations. The theme function allows you to adjust elements like fonts, colors, and grid lines to match your preferred style. For example, you can change the font size of axis labels, modify the background color, or remove grid lines for a cleaner look. The themebwa function provides a minimalist black and white theme that's often used in academic or print settings. Additionally, you can save custom themes for reuse across multiple plots, ensuring consistency in your work. This is particularly useful when you're preparing a presentation or report where visual coherence is key. By mastering theme customization, you'll be able to tailor your plots to suit different audiences and contexts. Handling overplotting and data density is a common challenge when visualizing large data sets. Overplotting occurs when too many points overlap, making it difficult to see patterns. One solution is to use jittering, which adds a small amount of random noise to points to spread them out. Transparency Alpha is another technique that allows you to see the density of points by making them partially transparent. For 2D distributions, GeomeHex creates hexagonal bins that show the count of points in each region, while Geome Density 2D generates contour lines to represent density. These methods help simplify complex scatter plots and reveal underlying trends. By applying these techniques, you can create clearer visualizations that effectively communicate the structure of your data. Let's now look at real-world examples of advanced visualizations. Time series data can be effectively visualized using GeomeLine for trends and GeomePoint to highlight specific data points. For instance, you might plot monthly sales data with a line to show overall trends and points to mark peak months. Heat maps are another powerful tool, created with GeomeTile and Scaleful Gradient to represent values with color gradients. This is ideal for visualizing matrices, such as correlation coefficients or geographical data. For geographic data, packages like ggmap integrate with mapping services to plot locations, while GeomePath can show routes or boundaries. These examples demonstrate how ggplot2 can be adapted to various domains, making it a versatile tool for data analysis. Finally, let's discuss best practices for creating advanced plots. Simplicity is key. Avoid clutter by focusing on the most important elements. Ensure that axes, titles, and legends are clearly labeled so that the plot is easy to interpret. For example, use descriptive axis labels and a legend that explains the meaning of different colors or shapes. Reproducibility is also crucial. Include comments in your code and save your scripts so others can follow your steps. Additionally, test your plots with different data sets to ensure they're robust and adaptable. By following these practices, you'll create visualizations that are not only informative, but also easy to understand and share. To wrap up, we've covered essential advanced techniques in ggplot2, including layering, faceting, and customization. These tools empower you to create sophisticated visualizations that enhance data analysis and communication. I encourage you to experiment with real data sets to apply what you've learned. Don't hesitate to explore additional packages like Plotly or ggvis for interactive visualizations, which can take your work to the next level. Remember, the goal of data visualization is to tell a story, and with practice, you'll become adept at turning complex data into clear, impactful insights. Thank you for your attention, and I look forward to seeing your creative applications of these techniques. Visual clarity is the cornerstone of effective data communication. When we present data, our goal is to ensure that the audience can quickly grasp the key messages without confusion. Poorly designed visuals can lead to misinterpretation, while clear and well-structured plots make complex information accessible. In R, there are multiple tools for customization, including Base R, which offers fundamental plotting functions, and ggplot2, which provides a more flexible and layered approach. Other libraries like Lattice or Plotly also contribute to advanced visualization. The primary objectives of customization are to enhance readability, emphasize critical insights, and maintain alignment with organizational branding. For instance, a marketing team might use specific colors and fonts to ensure consistency with their brand identity. By mastering these tools, we transform raw data into compelling narratives. Every plot requires attention to several key elements to ensure it communicates effectively. Titles, subtitles, and captions serve as the narrative framework, guiding the viewer through the data. A title might summarize the main finding, while a subtitle can provide additional context or limitations. Axis labels are essential for identifying what each axis represents, and tick marks help in pinpointing specific values. Grid lines add structure, making it easier to read the plot. Color schemes, fonts, and line styles contribute to the visual hierarchy, ensuring that important elements stand out. Legends must be placed thoughtfully to avoid clutter, and backgrounds can be adjusted to improve contrast. Finally, plot margins determine how much space surrounds the graph, affecting overall readability. These components work together to create a polished and professional appearance. ggplot2 revolutionizes plot customization through its layered approach, where each component of the plot is built incrementally. This allows for precise control over every aspect of the visualization. For example, the labs function is used to add titles, axis labels, and captions, making the plot self-explanatory. The theme function enables adjustments to non-data elements like fonts, colors, and spacing, ensuring a consistent style. Functions like scale let us manipulate the appearance of data layers, such as changing colors or shapes. By combining these tools, we can create highly tailored visualizations. For instance, a researcher might use labs to add a detailed title and theme to adjust font sizes for a presentation, ensuring the plot is both informative and visually appealing. Customizing axes and labels is crucial for tailoring the plot to the data being presented. The XLim and ILLim functions allow us to zoom in on specific ranges of data, which is useful for highlighting trends or anomalies. For continuous variables, scalx continuous and scala continuous let us define custom tick marks, labels, and breaks, making the plot more readable. Rotating axis labels with themexis. Text x equals element extangle equals 45 prevents overlapping text, especially when dealing with long labels. Annotations added via annotate or text can draw attention to specific data points or trends. For example, in a time series plot, rotating the x-axis labels to 45 degrees ensures they are legible, while an annotation might highlight a significant event. These adjustments ensure the plot is both functional and easy to interpret. Color is a powerful tool in data visualization, and ggplot2 provides extensive options for customizing it. The Scale Color Manual and Scaleful Manual functions allow us to specify exact color palettes, which is particularly useful when aligning with brand guidelines or ensuring accessibility. Built-in palettes like Virides offer perceptually uniform gradients that are easy to interpret, while our Color Brewer provides a range of color schemes suitable for different data types. Adjusting transparency with the alpha parameter helps in visualizing overlapping data points, such as in scatter plots. For continuous variables, gradient color scales, like those created with Scale Color Gradient, can represent values effectively. For instance, a heat map might use a gradient from blue to red to indicate increasing values, making patterns immediately visible. Themes in ggplot2 define the non-data elements of a plot, such as background colors, grid lines, and fonts. Built-in themes like Themigray, the default, provide a clean and professional look, while Themebwa offers a black and white alternative suitable for print. Themaminimal removes unnecessary elements, creating a modern, minimalist aesthetic. Understanding theme elements like panel background, which controls the plot area's background, or axis line, which defines the axis lines, allows for fine-tuned adjustments. Themes can be applied globally using ThemaSet or per plot, making it easy to maintain consistency across multiple visualizations. Saving custom themes ensures that they can be reused in future projects, streamlining the design process. Creating custom themes allows us to define a unique visual identity for our plots. Using the theme function, we can override default settings to match specific requirements. For example, element text can adjust fonts, sizes, and colors for titles, axis labels, and legends. Element line controls the appearance of lines, such as grid lines or axis borders. A custom theme for a publication might use a specific font like Times New Roman and a color scheme that aligns with the journal's guidelines. By combining multiple theme adjustments, we can create a cohesive look that enhances readability and professionalism. For instance, a theme might include a subtle background pattern, adjusted margins, and a consistent font size across all elements. Practical examples illustrate how customization transforms raw data into meaningful visuals. A bar chart might use labeled axes and a gradient fill to show variations in sales across regions, with the gradient indicating higher values. A scatter plot could be modified with a dark background theme to improve contrast and readability, especially in presentations with low lighting. Adding a custom logo or watermark to a plot ensures branding consistency, such as a company's emblem in the corner. Publication-ready figures often require adjusted margins to fit specific layout requirements, ensuring that the plot is both aesthetically pleasing and technically precise. These examples demonstrate how customization adapts plots to different contexts and audiences. Adhering to best practices ensures that customizations enhance rather than hinder data communication. Consistency is key. Using the same fonts, colors, and styles across all plots in a report or presentation creates a unified look. Avoiding excessive customization prevents clutter, allowing the data to take center stage. Readability-focused fonts like Arial or Helvetica, combined with high-contrast color schemes, make plots accessible to a wider audience. Documenting customizations, such as adding comments in the code, ensures that others can understand and reproduce the work. For example, a note explaining the choice of a particular color palette can help collaborators maintain the same visual style in future projects. mastering plot customization is essential for effective data communication. ggplot 2 offers a robust set of tools that allow for both fine-grained control and creative flexibility. Themes and manual adjustments enable the creation of visually striking and professional-looking plots tailored to specific needs. Whether it's a simple bar chart or a complex heat map, these techniques empower us to present data in ways that are both informative and engaging. By practicing these skills on real-world datasets, we can refine our ability to transform data into compelling stories. The next step is to apply these techniques. Experiment with different styles and continue exploring the vast possibilities of R for data visualization. Statistical analysis is the process of collecting, organizing, and interpreting data to uncover patterns, trends, and relationships. It plays a crucial role in data interpretation by transforming raw numbers into meaningful insights. Whether you are analyzing survey results, scientific experiments, or business metrics, statistical analysis helps you make informed decisions. R is a powerful programming language specifically designed for statistical computation and data visualization. It offers a vast array of built-in functions and libraries that simplify complex analyses. For instance, R can handle everything from basic calculations to advanced machine learning models. In this course, we will explore key topics such as descriptive statistics to summarize data, hypothesis testing to validate assumptions, regression analysis to model relationships, and inferential statistics to draw conclusions about populations from samples. Each of these areas will be covered with practical examples to ensure you can apply them confidently. To begin, let us discuss descriptive statistics, which provide a snapshot of your data. The mean or average is calculated by summing all values and dividing by the number of observations. The median represents the middle value when data is ordered, making it robust to outliers. While R does not have a built-in function for the mode, you can use the mode function or custom code to identify the most frequent value. The standard deviation measures the spread of data around the mean, with higher values indicating greater variability. In R, the mean function calculates the average, median finds the middle value, and SD computes the standard deviation. For a quick overview of your dataset, the summary function provides a concise summary, including the minimum, first quartile, median, mean, third quartile, and maximum. Visualizing data is equally important. Histograms, created with hist, display the distribution of numerical data by dividing it into bins. Box plots, generated using boxplot, show the spread and central tendency of data, highlighting outliers and skewness. These tools together give you a comprehensive understanding of your dataset's characteristics. Inferential statistics allows us to make generalizations about a population based on a sample. A population refers to the entire group of interest, while a sample is a subset of that population. Since it is often impractical to collect data from every individual in a population, we rely on samples to draw conclusions. Confidence intervals provide a range of values within which the true population parameter is likely to fall, typically expressed with a confidence level such as 95%. For example, a 95% confidence interval means that if we were to take 100 samples, the true value would lie within the interval for 95 of them. P-values, another critical concept, measure the strength of evidence against a null hypothesis. A small p-value, usually less than 0.05, suggests that the observed data is unlikely under the null hypothesis, leading us to reject it. Understanding these concepts is essential for making reliable inferences and avoiding misleading conclusions. Hypothesis testing is a structured method for evaluating assumptions about a population. The null hypothesis, denoted as H0, represents the default assumption that there is no effect or difference. The alternative hypothesis, H1, proposes that an effect or difference exists. For example, if testing a new drug, the null hypothesis might state that the drug has no impact, while the alternative suggests it does. Test statistics, such as the t-test or z-test, quantify how far the sample data deviates from the null hypothesis. In R, the t-test function performs t-tests for comparing means, while z-test is used for large samples. Interpreting p-values correctly is vital. A p-value less than the significance level, often 0.05, indicates sufficient evidence to reject the null hypothesis. However, it is important to remember that statistical significance does not always imply practical significance. Always consider the context and limitations of your data when drawing conclusions. R offers several common statistical tests to address different research questions. The t-test is used to compare the means of two groups, such as testing whether a new teaching method improves student performance. The t-test function in R automates this process, providing the test, statistic, p-value, and confidence interval. For comparing more than two groups, ANOVA analysis of variance is the go-to method. The ANOVA function in R conducts ANOVA, determining if there are statistically significant differences between group means. When dealing with categorical data, the chi-square test, implemented via KISK test, assesses whether observed frequencies differ from expected frequencies. For instance, it can test if there is an association between gender and voting preferences. Each test has specific assumptions, such as normality for t-tests or independence for chi-square, which should be checked to ensure valid results. Regression analysis is a fundamental tool for modeling relationships between variables. Simple linear regression, using the LM function in R, fits a straight line to the data, expressing the dependent variable as a function of the independent variable. The equation takes the form y equals a plus bx, where a is the intercept and b is the slope. Interpreting the output involves examining coefficients, which indicate the change in the dependent variable for a 1-unit change in the independent variable. The R-squared value represents the proportion of variance explained by the model, with higher values indicating a better fit. P-values for coefficients help determine if the relationship is statistically significant. Visualizing regression results is equally important. The plot function in R generates scatter plots with regression lines, while residual plots help assess model assumptions like linearity and homoscedasticity. These tools enable you to evaluate and refine your models effectively. To recap, this course has covered essential statistical concepts in R, from descriptive statistics to inferential methods and regression analysis. You have learned how to summarize data, test hypotheses, and model relationships using real-world examples. Practicing with diverse data sets is crucial for mastering these techniques. I encourage you to explore datasets from public repositories or your own projects to apply what you've learned. As you progress, consider delving into advanced topics like machine learning in R, which builds on these foundations to predict outcomes and uncover complex patterns. R's extensive ecosystem of packages such as Carrot for machine learning or ggplot2 for advanced visualizations, offers endless opportunities for further exploration. Keep experimenting, stay curious, and let your data tell its story. Descriptive statistics serve as the foundation for understanding and summarizing the essential characteristics of a dataset. By using these techniques, we can distill complex information into meaningful insights, making it easier to identify patterns, trends, and anomalies within the data. This process is critical in data analysis because it allows us to form a clear picture of the data before diving into more advanced statistical methods. The key components of descriptive statistics include central tendency, which helps us find the typical or central value in a dataset, dispersion, which measures how spread out the data points are, and distribution, which describes the shape and variation of the data. Together, these elements provide a comprehensive overview of the dataset's properties. When analyzing data, measures of central tendency are essential for identifying the central or typical value within a dataset. The mean, often referred to as the average, is calculated by summing all the values and dividing by the number of observations. However, the mean can be influenced by extreme values, making it less reliable in skewed distributions. The median, on the other hand, represents the middle value when the data is ordered from smallest to largest, making it a more robust measure in such cases. The mode is the value that appears most frequently in the dataset, which is particularly useful for categorical or discrete data. Choosing the appropriate measure depends on the nature of the data and its distribution, ensuring that the insights derived are accurate and meaningful. Measures of dispersion provide critical information about the spread or variability of a dataset, complementing the insights from central tendency. The range is the simplest measure, calculated as the difference between the maximum and minimum values, but it is sensitive to outliers. Variance quantifies the average squared deviation of each data point from the mean, offering a more comprehensive view of variability. However, because variance is expressed in squared units, it can be difficult to interpret directly. The standard deviation, which is the square root of the variance, resolves this issue by returning to the original units of measurement, making it more intuitive. The interquartile range, or IQR, measures the spread of the middle 50% of the data, making it a robust, alternative to the range when dealing with skewed or outlier-prone datasets. In R, several built-in functions simplify the calculation of descriptive statistics. The summary function provides a quick overview of a dataset, returning the minimum, maximum, quartiles, mean, and median in a single call. For specific metrics, the mean function calculates the average, while the median function identifies the middle value. The SD function computes the standard deviation, and the var function calculates the variance. The quantile function allows for the extraction of specific percentiles, such as the 25th, 50th, and 75th percentiles, offering flexibility in analyzing data distribution. Finally, the table function generates frequency counts for categorical variables, making it ideal for summarizing discrete data. These functions are invaluable tools for efficiently analyzing and interpreting datasets. Visualizing summary metrics enhances our ability to interpret data by transforming numerical summaries into intuitive graphical representations. Histograms display the distribution of numerical data by dividing it into bins and showing the frequency of values within each range. Box plots, also known as box and whisker plots, illustrate key statistics such as quartiles, the median, and potential outliers, providing a clear view of data spread and central tendency. Density plots offer a smoothed version of histograms, revealing trends in the data distribution without the influence of bin size. Scatter plots, meanwhile, are used to explore relationships between two numerical variables, helping identify correlations or patterns that may not be apparent from summary statistics alone. These visual tools complement quantitative measures, enabling a more holistic understanding of the data. Handling missing data is a crucial step in ensuring the accuracy and reliability of descriptive statistics. Missing values can be identified using functions like ISNA, which returns a logical vector indicating where missing values occur, or complete cases, which identifies rows with no missing data. Strategies for addressing missing data include removing incomplete observations, imputing missing values using methods such as mean substitution or predictive modeling, or leveraging functions that allow for the exclusion of missing values, such as NARM equals true in the mean function. Ignoring missing data can lead to biased or misleading results, so it is essential to carefully consider the appropriate approach based on the data set and analysis goals. Properly handling missing values ensures that summary metrics reflect the true characteristics of the data. Descriptive statistics form the cornerstone of data analysis, providing the foundational insights needed to explore and understand datasets effectively. R offers a wide array of functions and tools to calculate and visualize these statistics, making it a powerful environment for data exploration. Before proceeding with more complex analyses, it is vital to validate data quality by checking for missing values and ensuring that the data is representative and accurate. Additionally, selecting the appropriate measures of central tendency and dispersion based on the data type and distribution ensures that the insights derived are both meaningful and reliable. By mastering these concepts, analysts can lay a strong groundwork for further statistical investigations and informed decision-making. Probability distributions describe the likelihood of possible outcomes in an experiment. For example, if you flip a coin multiple times, the distribution would show the probabilities of getting heads or tails. In R, built-in functions handle common distributions such as normal, binomial, and Poisson. These functions allow you to calculate probabilities, generate random data, and analyze distributions efficiently. The key functions in R are D for density, P for cumulative probability, Q for quantile, and R for random generation. Understanding these distributions is critical for statistical analysis and modeling because they form the foundation for making inferences, testing hypotheses, and building predictive models. Whether you are working with continuous data like heights or discrete events like coin flips, mastering these functions will enhance your ability to interpret and analyze data effectively. Common probability distributions in R include the normal distribution, binomial distribution, Poisson distribution, exponential distribution, and uniform distribution. For each of these, R provides a set of functions with the same prefix. For the normal distribution, the functions are d-norm, p-norm, q-norm, and r-norm. The binomial distribution uses d-binom, p-binom, q-binom, and r-binom. The Poisson distribution has d-poise, p-poise, q-poise, and r-poise. The exponential distribution is handled by dexp, pexp, kexp, and rexp, while the uniform distribution uses dunif, punif, quinif, and runif. These functions allow you to perform tasks like calculating the probability density, finding cumulative probabilities, determining quantiles, or generating random samples. Each distribution is tailored to specific types of data and scenarios, making them essential tools for statistical analysis. The density function in R, denoted by the letter D, calculates the probability density of a specific value in a distribution. For example, D norm 0, mean equals 0, standard deviation equals 1 gives the probability density at the value 0 for a standard normal distribution. The cumulative probability function, denoted by P, calculates the probability that a random variable is less than or equal to a given value. For instance, P norm 1.96 returns the probability that a value is less than or equal to 1.96 in a standard normal distribution. The quantile function, represented by Q, finds the value corresponding to a given cumulative probability. For example, Q norm 0.95 returns the 95th percentile of a normal distribution. The random generation function, denoted by R, produces random samples from a specified distribution. An example is R norm 100, which generates 100 random numbers from a standard normal distribution. These functions are consistent across all distributions, making them easy to use once you understand their purpose. Let us explore the normal distribution in R with an example. To generate 1,000 random samples from a normal distribution with a mean of 50 and a standard deviation of 10, you can use the command rnorm 1000, mean equals 50, standard deviation equals 10. This creates a dataset that follows a bell-shaped curve. To visualize the distribution, you can plot a histogram using hist rnorm 1000. Color equals light blue. Main equals normal distribution. This histogram shows the frequency of values across the range of the distribution. Additionally, you can calculate the cumulative probability up to a specific value. For example, P norm 60, mean equals 50, standard deviation equals 10, gives the probability that a value is less than or equal to 60 in this normal distribution. These steps help you understand the characteristics of the data and make informed decisions based on the distribution. The binomial distribution is used to model the number of successes in a fixed number of independent trials with the same probability of success. For instance, to calculate the probability of getting exactly 5 successes in 10 trials with a probability of success of 50%, you can use dbinom 5, size equals 10, prob equals 0.5. This returns the probability of exactly 5 successes. To find the cumulative probability of 5 or fewer successes, you can use p-binom 5, size equals 10, prob equals 0.5. This tells you the probability of observing 5 or fewer successes. To generate 100 binomial random samples, you can use r-binom 100, size equals 10, prob equals 0.5. This creates a data set that follows a binomial distribution, which is useful for simulating scenarios like coin flips or quality control processes. Visualizing distributions in R helps you understand their shape, central tendency, and variability. You can use the plot function or specialized libraries like ggplot2 to create visualizations. For example, a density plot can show the probability density of values in a distribution. To create a density plot, you might use density rnorm 1000, then plot the result. Another useful visualization is the quantile plot, or QQ plot, which compares the distribution of your data to a theoretical distribution. In R, you can generate a QQ plot using QQ norm and QQ line. These visualizations help you assess whether your data follows a specific distribution, identify outliers, and make data-driven decisions. By combining plots with statistical functions, you can gain deeper insights into your data. Probability distributions have numerous real-world applications. For example, in finance, the normal distribution is used to model stock returns, while the Poisson distribution can predict the number of customer arrivals at a store. In hypothesis testing, distributions help determine the likelihood of observing a particular result under the null hypothesis. Simulations using distributions allow researchers to model complex systems, such as weather patterns or disease spread. Predictive modeling relies on distributions to estimate probabilities and make forecasts. Whether you are analyzing survey data, optimizing processes, or developing machine learning models, understanding distributions is essential. By leveraging R's built-in functions, you can efficiently apply these concepts to solve practical problems and make data-driven decisions. In summary, probability distributions are fundamental to statistical analysis and modeling. R provides a comprehensive set of functions for working with distributions, including density, cumulative probability, quantile, and random generation. These functions are consistent across different distributions, making them easy to use once you understand their purpose. By applying these tools, you can analyze data, visualize patterns, and make informed decisions. Whether you are a student, researcher, or data scientist, mastering these concepts will enhance your ability to work with data effectively. The examples and techniques discussed today demonstrate how R can simplify complex statistical tasks, enabling you to explore and interpret data with confidence. Hypothesis testing is a fundamental statistical method used to evaluate claims about population parameters. These parameters could be things like the average value of a variable in a population or the proportion of a certain category. The purpose of hypothesis testing is to determine whether the evidence from a sample of data supports or refutes a specific claim. To do this, we rely on 4 key components. The first is the null hypothesis, which is a statement that assumes no effect or no difference in the population. The second is the alternative hypothesis, which represents the claim we are trying to test. The third component is the significance level, often denoted by the Greek letter alpha, which sets the threshold for deciding whether to reject the null hypothesis. Finally, we use the p-value, which quantifies the strength of evidence against the null hypothesis based on the observed data. The process of hypothesis testing follows a structured sequence of steps. First, we must clearly state the null hypothesis and the alternative hypothesis. The null hypothesis typically represents a default position, such as no effect, while the alternative hypothesis suggests a specific relationship or difference. Next, we choose a significance level, which is a probability threshold that determines how extreme the data must be for us to reject the null hypothesis. Common values for this threshold include 0.05, 0.01, and 0.1, each reflecting different levels of confidence. After defining these, we collect data from a sample and calculate a test statistic, which measures how far the sample data deviates from what we would expect under the null hypothesis. We then determine the p-value or critical value, which helps us assess the likelihood of observing the data if the null hypothesis were true. Finally, we make a decision based on these results, either rejecting the null hypothesis or failing to reject it. The null hypothesis and alternative hypothesis form the foundation of any hypothesis test. The null hypothesis, often denoted as H0, assumes that there is no effect or no difference in the population. For example, if we are testing whether a new drug has an impact, the null hypothesis might state that the drug has no effect. The alternative hypothesis, denoted as H1, represents the claim we are testing. In the drug example, this could be that the drug does have an effect. These hypotheses are mutually exclusive and exhaustive, meaning only one can be true. A common example is a two-tailed test, where the alternative hypothesis states that the population parameter is not equal to a specific value. For instance, H0 might state that the mean value of a population is 10, while H1 claims the mean is not 10. This setup allows us to detect effects in either direction. The significance level, or alpha, plays a critical role in hypothesis testing by defining the threshold for rejecting the null hypothesis. This value represents the probability of making a type I error, which is incorrectly rejecting a true null hypothesis. For example, if we set alpha to 0.05, there is a 5% chance of concluding there is an effect when there is actually none. Critical values are used to determine the boundaries of the rejection region, which is the range of test statistics that would lead us to reject the null hypothesis. These values depend on the chosen significance level and the distribution of the test statistic. Common significance levels like 0.05, 0.01, and 0.1 are used in different contexts to balance the risk of type I errors with the need for sensitivity in detecting true effects. Test statistics are calculated values that summarize the relationship between the sample data and the null hypothesis. They measure how far the observed data deviates from what would be expected under the null hypothesis. For example, a z-test is used when the population's standard deviation is known, while a t-test is used when it is unknown and the sample size is small. The chi-square test is applied to categorical data to assess independence or goodness of fit. Each test statistic corresponds to a specific distribution, such as the normal distribution for z-tests, the t-distribution for t-tests, and the chi-square distribution for chi-square tests. Understanding these distributions helps us interpret the test statistic and determine its significance. The p-value is a crucial concept in hypothesis testing, representing the probability of observing the data, or something more extreme, if the null hypothesis is true. It quantifies the strength of the evidence against the null hypothesis. A smaller p-value indicates stronger evidence against the null hypothesis, suggesting that the observed data is unlikely under the assumption of no effect. For instance, a p-value of 0.01 means there is a 1% chance of obtaining the observed results if the null hypothesis were true. Importantly, the p-value does not measure the probability that the null hypothesis is true or the probability that the alternative hypothesis is true. Instead, it provides a measure of compatibility between the data and the null hypothesis. Interpreting p-values involves comparing them to the chosen significance level. If the p-value is less than or equal to alpha, we reject the null hypothesis, concluding that the results are statistically significant. This suggests that the observed data is unlikely under the null hypothesis. Conversely, if the p-value is greater than alpha, we fail to reject the null hypothesis, indicating that the data does not provide sufficient evidence to support the alternative hypothesis. For example, if the p-value is 0.03 and alpha is 0.05, we reject the null hypothesis because the evidence against it is strong enough. However, it is important to note that failing to reject the null hypothesis does not prove it is true. It simply means the data does not provide enough evidence to disprove it. In R, calculating p-values is straightforward using built-in functions. For example, the t-test function performs a t-test and returns the p-value as part of its output. Similarly, the prop test function is used for proportions, such as testing whether a sample proportion differs from a hypothesized value. To extract the p-value from a test result, we can use the p-value attribute. For instance, t test data $p value would return the p-value for a t-test conducted on the data vector. These functions automatically handle the calculations, allowing users to focus on interpreting the results. It is essential to ensure the correct parameters are specified, such as the type of test, one-tailed or two-tailed, and the data structure. Hypothesis testing is applied in various scenarios to address different research questions. For example, a t-test can be used to determine whether a new drug has a significant effect on patient outcomes by comparing the mean scores of a treatment group and a control group. When comparing proportions between groups, such as the success rates of two different marketing strategies, a chi-square test is appropriate. Another common application is assessing whether a coin is fair by using a binomial test to check if the observed number of heads and tails aligns with the expected 50-50 distribution. Each test is tailored to the type of data and the specific hypothesis being tested, ensuring accurate and meaningful conclusions. Hypothesis testing provides a structured framework for making data-driven decisions in research and analysis. By using p-values, we can quantify the evidence against the null hypothesis and make informed choices about the validity of our claims. However, it is crucial to interpret these results carefully, avoiding over-reliance on arbitrary significance thresholds like alpha. Context, sample size, and effect size all play important roles in determining the practical significance of findings. Ultimately, hypothesis testing serves as a powerful tool for uncovering patterns in data, while remaining mindful of its limitations and the broader implications of statistical decisions. Regression analysis is a statistical method used to explore relationships between variables. It helps us understand how one variable, called the dependent variable, changes in response to other variables, known as independent variables. For example, if we want to predict a person's height based on their age, height would be the dependent variable, and age would be the independent variable. Regression is widely used in forecasting, such as predicting sales trends, analyzing patterns in data, and even determining cause and effect relationships in scientific studies. The key components of regression include the dependent variable, often denoted as y, the independent variables, typically represented as x, and an error term, which accounts for the variability in the dependent variable that cannot be explained by the independent variables. This error term is crucial because it acknowledges that no model is perfect, and there are always unmeasured factors influencing the outcome. There are several types of regression models, each suited for different scenarios. Linear regression is the simplest form, modeling a straight-line relationship between the dependent variable and one or more independent variables. For instance, if we have a single independent variable, the equation would look like y equals beta 0 plus beta 1x plus epsilon, where beta 0 is the intercept, beta 1 is the slope, and epsilon is the error term. When there are multiple independent variables, we use multiple regression, which allows us to analyze the impact of several factors simultaneously. Logistic regression, on the other hand, is used when the dependent variable is binary, such as predicting whether a customer will buy a product, yes or no. Polynomial regression extends linear regression by incorporating higher-order terms like x squared or x cubed to capture nonlinear relationships. For example, if we are modeling the growth of a plant over time, a quadratic term might better represent the slowing growth rate as the plant matures. Each model has its own assumptions and applications, making it essential to choose the right one based on the data and research question. Building a regression model involves several critical steps. The first is data preparation, which includes cleaning the data by handling missing values, removing duplicates, and encoding categorical variables. For example, if we have a variable like gender with categories male and female, we might convert it into numerical values like 0 and 1. Next, we fit the model using functions like LM for linear models or GLM for generalized models, which can handle different types of dependent variables, such as binary or count data. After fitting the model, it is vital to check the underlying assumptions to ensure the results are reliable. These assumptions include linearity, meaning the relationship between variables is straight, normality of residuals, homoscedasticity, which refers to constant variance in the errors, and independence, ensuring that observations are not correlated. Finally, we evaluate the model's performance using metrics like R-squared, which measures how much of the variance in the dependent variable is explained by the model adjusted R-squared, which accounts for the number of predictors, and p-values, which indicate the significance of individual predictors. These steps help create a robust and accurate model. Interpreting regression output requires understanding several key components. The coefficients in the model represent the change in the dependent variable for a 1-unit change in the corresponding independent variable, assuming all other variables are held constant. For example, if the coefficient for advertising spend is 2.5, this means that for every additional dollar spent on advertising, sales are expected to increase by $2.50, all else being equal. P-values test the statistical significance of each predictor, with values less than 0.05, typically indicating that the variable has a meaningful impact on the dependent variable. R-squared tells tells us the proportion of the variance in the dependent variable that is explained by the independent variables. However, it is important to note that a high R-squared does not always mean a good model, as it can be inflated by adding more predictors. The F statistic, on the other hand, tests the overall significance of the model, determining whether at least one predictor is significantly related to the dependent variable. Together, these elements provide a comprehensive view of the model's effectiveness and reliability. Model diagnostics and validation are essential to ensure the accuracy and generalizability of regression results. Residual analysis involves examining the differences between observed and predicted values to detect patterns that may indicate model inadequacies. For instance, if the residuals form a clear pattern rather than being randomly scattered, it suggests that the model may not be capturing all the relevant relationships. Multicollinearity, which occurs when independent variables are highly correlated, can distort the results and make it difficult to assess the individual effect of each predictor. To address this, we use the variance inflation factor, which quantifies how much the variance of a coefficient is increased due to correlations with other variables. Cross-validation is another technique where the data is split into training and test sets to evaluate how well the model performs on new, unseen data. This helps prevent overfitting, a situation where the model performs well on the training data, but poorly on new data. Overfitting can be avoided by simplifying the model, reducing the number of predictors, or using techniques like regularization, which penalizes overly complex models. These diagnostics ensure that the model is both accurate and reliable. Regression analysis has a wide range of applications in R, making it a powerful tool for data-driven decision-making. For example, businesses use regression to predict sales based on advertising spend, helping them allocate budgets more effectively. In education, researchers analyze factors affecting student performance, such as study hours, socioeconomic status, or teacher quality, to identify areas for improvement. In healthcare, regression models can predict disease risk by analyzing patient data like age, blood pressure, or family history. Advanced techniques, such as regularization methods like ridge and lasso regression, are implemented using the GLNet package in R. These methods help prevent overfitting by adding a penalty to the model's complexity, making them particularly particularly useful when dealing with large data sets with many predictors. By applying regression to real-world problems, analysts can uncover valuable insights and make informed decisions. Regression analysis is a fundamental tool in both predictive and explanatory modeling, offering a structured approach to understanding relationships in data. Choosing the appropriate model type and rigorously validating its assumptions are critical steps in ensuring the reliability of the results. Practicing with real data sets allows learners to apply theoretical concepts in practical scenarios, enhancing their proficiency in R, for instance. Working with datasets from public repositories or industry-specific projects can provide hands-on experience in data cleaning, model building, and interpretation. Continuous learning is also essential, as the field of statistics and data science is constantly evolving. Exploring advanced topics like nonlinear models, machine learning integration, or Bayesian regression can further expand one's capabilities. By combining theoretical knowledge with practical application, individuals can harness the full potential of regression analysis to solve complex problems and drive meaningful insights. Machine learning is a powerful branch of artificial intelligence that focuses on creating systems capable of learning from data rather than relying on explicit programming. This means that instead of writing code that dictates every step, we allow algorithms to identify patterns and make decisions based on the information they process. For example, in image recognition, a machine learning model can learn to distinguish between cats and dogs by analyzing thousands of labeled images. In natural language processing, it can understand and generate human language, like translating text or summarizing articles. Predictive analytics is another key area where machine learning helps forecast future trends, such as predicting customer behavior or stock market movements. The goal of machine learning is to build models that improve over time as they are exposed to more data, making them increasingly accurate and efficient in their tasks. There are 3 primary types of machine learning, each with distinct approaches and applications. The first is supervised learning, where the algorithm learns from labeled data. This means each training example has an input and a corresponding output, like a data set where house prices are paired with features such as square footage and location. Common techniques here include regression, which predicts continuous values, and classification, which assigns categories to data points. The second type is unsupervised learning, which deals with unlabeled data. Here, the algorithm identifies hidden patterns or structures on its own, such as clustering similar customers together for targeted marketing, or reducing the number of variables in a dataset to simplify analysis. The third type is reinforcement learning, where an agent learns by interacting with an environment to maximize rewards. Think of a robot learning to walk, or a game-playing AI improving its strategy through trial and error. Each type of machine learning has unique strengths, and choosing the right one depends on the problem at hand and the data available. Understanding key concepts in machine learning is essential for building effective models. Features are the input variables used to make predictions, such as age, income, or temperature in a dataset. Labels are the output variables that the model aims to predict, like whether an email is spam or not. Training data is the dataset used to teach the model, where it learns the relationships between features and labels. Test data, on the other hand, is a separate set of data used to evaluate how well the model performs on new, unseen examples. It's crucial to split data into training and test sets to ensure the model generalizes well and isn't just memorizing the training data. Another important concept is the difference between training and testing phases. Training is where the model learns, and testing is where it proves its ability to apply what it has learned. These concepts form the foundation of any machine learning project and guide the entire process from data preparation to model evaluation. Several algorithms are commonly used in machine learning, each suited for different tasks. Linear regression is a simple yet powerful technique for predicting continuous outcomes, such as estimating house prices based on features like size and location. It works by fitting a straight line to the data, but it assumes a linear relationship between variables, which might not always hold. Decision trees are another popular method, where the data is split into branches based on feature thresholds, making it easy to visualize and interpret. For instance, a decision tree might first check a customer's age, and then their income to decide if they are likely to purchase a product. K-nearest neighbors, or KNN, classifies data points by comparing them to their nearest neighbors in the feature space. This method is intuitive, but can be computationally intensive for large datasets. Support vector machines, or SVMs. Find the optimal boundary between classes by maximizing the margin between them, making them effective for complex, high-dimensional data. Each algorithm has its advantages and limitations, and selecting the right one often depends on the specific problem and data characteristics. Evaluating a machine learning model's performance is critical to ensure it works effectively in real-world scenarios. Accuracy measures the proportion of correct predictions out of all predictions made, but it can be misleading if the data is imbalanced. For example, in a dataset where 95% of emails are not spam, a model that always predicts not spam would have high accuracy but fail to detect actual spam. Precision and recall are more nuanced metrics for classification tasks. Precision focuses on the proportion of true positive predictions among all positive predictions, ensuring that when the model says something is positive, it is correct. Recall, on the other hand, measures the proportion of true positives identified out of all actual positives, ensuring the model doesn't miss important cases. The F1 score combines precision and recall into a single metric, providing a balanced view of a model's performance. Cross-validation is another technique that enhances reliability by splitting the data into multiple subsets, training the model on some and testing on others, then averaging the results. This reduces the risk of overfitting and gives a more accurate assessment of how the model will perform on new data. Mastering machine learning requires a solid understanding of data, algorithms, and evaluation techniques. In R, there are powerful tools like the carrot package, which streamlines the process of building and evaluating models, and random forest for creating ensembles of decision trees to improve accuracy. The GLM function is used for generalized linear models, extending regression to different types of outcomes. However, theory alone isn't enough. Practicing with real-world datasets is essential to apply these concepts effectively. By working on practical problems, such as predicting customer churn or analyzing social media trends, learners can develop the skills needed to tackle complex challenges. Remember, machine learning is an iterative process, and continuous practice with diverse datasets will deepen your understanding and proficiency in this exciting field. Building and evaluating models is a fundamental aspect of data science and statistical analysis. In R, model development involves a structured approach to create predictive systems that can make informed decisions based on data. The importance of model evaluation cannot be overstated because it ensures that the models we build are not only accurate but also reliable when applied to new, unseen data. This process helps us avoid pitfalls like overfitting and ensures that our models generalize well. The key objectives of this training include mastering the steps to build a model, testing its effectiveness, and refining it through iterative improvements. By the end of this course, you will have a solid understanding of how to develop, assess, and enhance predictive models using ARC. The first step in building a model is data preparation, which involves cleaning the data to handle missing values, outliers, and inconsistencies. Transformation may include scaling, normalization, or encoding categorical variables. Feature selection is also critical, as it helps identify the most relevant variables that contribute to the model's performance. Once the data is ready, the next step is choosing an appropriate algorithm. For example, linear regression is ideal for continuous outcomes, while decision trees are useful for handling nonlinear relationships. Splitting the data into training and testing sets allows us to evaluate the model's performance on data it has not seen before. In R, packages like Carrot and Tita models provide powerful tools to streamline this process, making it easier to train models efficiently. R offers a wide range of modeling techniques tailored to different types of problems. Linear regression is a foundational method for predicting continuous variables, such as house prices or sales figures. Logistic regression, on the other hand, is used for binary classification tasks, like predicting whether a customer will churn or not. For more complex datasets, ensemble methods like random forests and gradient boosting can capture intricate patterns and improve accuracy. These techniques combine multiple models to reduce errors and enhance performance. Neural networks, which mimic the structure of the human brain, are particularly effective for nonlinear relationships and large datasets. Each technique has its strengths and weaknesses, and the choice depends on the nature of the problem and the data available. Evaluating model performance is essential to determine how well a model can predict outcomes. For regression tasks, common metrics include root mean squared error, which measures the average magnitude of errors, and mean absolute absolute error, which provides a straightforward average of absolute differences. R squared, or the coefficient of determination, indicates how well the model explains the variability in the data. In classification problems, accuracy measures the proportion of correct predictions, while precision and recall focus on the model's ability to correctly identify positive cases and avoid false negatives. The F1 score balances precision and recall, offering a single metric for models with class imbalances. A confusion matrix visually represents the model's performance by showing true positives, false positives, true negatives, and false negatives. Cross-validation is a robust technique to assess how well a model generalizes to new data. K-fold cross-validation divides the dataset into K subsets, trains the model on K1 subsets, and tests it on the remaining one. This process repeats K times, ensuring that every data point is used for both training and testing. This method provides a more reliable estimate of model performance compared to a single train test split. For imbalanced datasets, stratified sampling maintains the proportion of classes in each fold, preventing the model from being biased toward the majority class. Leave one out cross-validation, where each data point is tested individually, is particularly useful for small datasets, but can be computationally intensive. These techniques help us build models that are resilient to overfitting and perform consistently across different data scenarios. Model tuning and optimization involve adjusting hyperparameters to improve performance. Hyperparameters, such as learning rates or tree depths, are not learned from the data, but set by the user. Grid search and random search are popular methods for exploring hyperparameter combinations. Grid search systematically tests all possible values, while random search samples from a defined distribution, often finding good solutions faster. Packages like Tune and MLR in R automate this process, making it easier to find the optimal settings. Balancing the bias-variance trade-off is critical, as models with high bias underfit the data, while those with high variance overfit. By fine-tuning these parameters, we can achieve a model that is both accurate and generalizable. Interpreting model results is crucial for understanding how predictions are made. In linear models, coefficients indicate the relationship between variables, showing how a unit change in an input affects the output. For tree-based models like random forests feature importance scores highlight which variables contribute most to the predictions. This helps identify key drivers of the outcome. SHAP values, or S-happily additive explanations, provide a more detailed breakdown of individual predictions. By considering the contribution of each feature, these tools are invaluable for explaining model behavior to stakeholders and ensuring transparency, especially in critical applications like healthcare or finance. Model evaluation comes with several challenges that can affect reliability. Overfitting occurs when a model learns the training data too well, capturing noise instead of the underlying pattern, leading to poor performance on new data. Data leakage is another common issue, where information from outside the training set unintentionally influences the model, creating an overly optimistic evaluation. Imbalanced datasets, where one class dominates, can skew metrics like accuracy, making it difficult to assess true performance. Addressing these challenges requires careful data handling, appropriate evaluation metrics, and techniques like resampling or synthetic data generation to ensure models are robust and fair. Let's explore a real-world case study on predicting customer churn. The process begins with data preprocessing, where we clean the dataset, handle missing values, and encode categorical variables. Next, we select appropriate models, such as logistic regression or random forests, and split the data into training and testing sets. After training the model, we evaluate its performance using metrics like accuracy and the confusion matrix. Finally, we interpret the results to understand which factors influence churn and refine the model based on insights. This case study highlights the importance of each step, from data preparation to model interpretation, and demonstrates how adjustments can improve predictive power and business outcomes. Adhering to best practices ensures that models are both effective and reproducible. Validating models with unseen data is essential to gauge their real-world performance. Documenting every step, from data preprocessing to hyperparameter tuning, allows others to replicate the process and build upon the work. Iteration is key, as models should be continuously refined based on feedback, new data, and changing requirements. By following these practices, we create models that are not only accurate, but also transparent, reliable, and and adaptable to evolving challenges in data science. Building and evaluating models is a cornerstone of data science, enabling us to make informed decisions and derive insights from data. R provides a rich ecosystem of tools and packages that simplify this process, from model training to evaluation and interpretation. As you progress in your training, remember that practice and continuous learning are vital to mastering these skills. By applying the concepts and techniques discussed, you will be well equipped to develop models that drive meaningful outcomes in various domains. Keep exploring, experimenting, and refining your approach to become a proficient modeler. Debugging and troubleshooting code is an essential skill for any R programmer. It involves identifying and resolving issues in your code to ensure it runs as expected. This session will guide you through the fundamentals of debugging in R, common errors you may encounter, and the tools and techniques to effectively troubleshoot problems. By understanding how to debug, you can save time, improve code reliability, and gain deeper insights into how your programs function. Let's begin by exploring the different types of errors that can arise in R code. Common errors in R code can be categorized into 4 main types. Syntax errors occur when the code violates R's grammar rules, such as missing parentheses, incorrect function names, or improper use of operators. These are often the easiest to spot because R will typically highlight them with error messages. Logical errors, on the other hand, are more subtle. They happen when the code runs without crashing, but produces incorrect results due to flawed logic, such as a miscalculation or an improper algorithm. Runtime errors occur during execution, like division by 0 or trying to access a variable that doesn't exist. Environmental errors are related to the R environment itself, such as missing libraries, incorrect file paths, or misconfigured working directories. Each type of error requires a different approach to resolve, so recognizing them is the first step in debugging. R provides several built-in tools to aid in debugging. The browser function allows you to pause the execution of your code at a specific point, letting you inspect variables and step through the code line by line. This is particularly useful for understanding how data changes as your code runs. The traceback function helps identify the source of runtime errors by showing the sequence of function calls that led to the error. The debug function enables you to step through a function's code as it executes, making it easier to pinpoint where things go wrong. Finally, the options error function lets you customize how R handles errors, such as logging them to a file or displaying a specific message. These tools, when used together, can significantly streamline the debugging process. To troubleshoot effectively, start by isolating the problem. Test small segments of your code to determine where the issue arises. This reduces complexity and makes it easier to identify the root cause. Using print statements or the cat function to output variable values can help trace how data is being processed. RStudio's debugging interface offers a visual way to set breakpoints, step through code, and inspect objects, making it a powerful tool for interactive debugging. Additionally, consulting R's extensive documentation and community forums like Stack Overflow can provide insights into common issues and solutions. Remember, troubleshooting is as much about patience as it is about technical skills. Let's look at real-world examples of debugging. For instance, a function with a typo in variable names might produce unexpected results. By carefully checking each variable reference, you can correct the issue. An infinite loop often stems from a condition that never evaluates to false. So reviewing loop logic and incrementing variables is key. Data import issues, such as incorrect file paths or encoding problems, can be resolved by verifying the file location and specifying the correct encoding format. These case studies highlight how systematic analysis and the right tools can turn frustrating problems into manageable tasks. In conclusion, debugging is a critical component of writing robust R code. It requires a combination of tools like browser and traceback, alongside logical analysis to identify and fix issues. By practicing troubleshooting regularly, you'll become more efficient and confident in your coding abilities. Remember, even experienced programmers encounter errors, but the ability to debug effectively sets apart a good coder from a great one. Keep experimenting, stay curious, and let debugging become a natural part of your workflow. Performance optimization in R refers to the process of improving the speed and efficiency of your code to handle tasks more effectively. This is particularly important when working with large data sets or performing complex computations, as inefficient code can lead to long processing times and excessive resource consumption. Common bottlenecks in our code often include the use of loops, which are generally slower compared to vectorized operations, high memory usage due to unnecessary data duplication, and the use of functions that are not optimized for performance. By addressing these issues, you can significantly enhance the responsiveness and scalability of your R programs. One of the fundamental principles of writing efficient R code is to prioritize vectorization over loops. Vectorized operations allow R to perform computations on entire vectors or matrices at once, which leverages the underlying C and Fortran code for faster execution. Another key principle is to minimize object copying, as creating unnecessary copies of data can consume memory and slow down your code. Instead, use in-place modifications where possible. Additionally, built-in functions such as apply, deepler, and other tidyverse tools are often optimized for performance, making them preferable to custom loops or less efficient implementations. These practices not only improve speed, but also make your code more concise and readable. Effective memory management is crucial for optimizing R code, especially when dealing with large datasets. The garbage collection function GC can be used to manually trigger memory cleanup, freeing up resources that are no longer in use. Avoiding unnecessary data duplication is another important strategy. For example, using data table indexing instead of the subset function can prevent the creation of new data objects, thereby reducing memory overhead. Lightweight data structures like data table are designed to handle large data sets more efficiently than traditional data frames, making them a better choice for memory-intensive tasks. By managing memory proactively, you can prevent your R sessions from becoming sluggish or crashing due to resource constraints. To identify performance issues in your R code, you can use profiling and benchmarking tools. The rprof function allows you to record the time spent in different parts of your code, helping you pinpoint slow functions. The profvis package provides a visual interface for analyzing these profiles, making it easier to understand where optimizations are needed. For benchmarking, the micro benchmark and bench packages enable you to compare the execution time of different code implementations. By systematically profiling and benchmarking your code, you can make data-driven decisions about where to focus your optimization efforts, ensuring that changes actually improve performance. Replacing loops with vectorized operations is one of the most effective ways to improve our code performance. For instance, instead of using a for loop to sum elements in a vector, you can use the built-in sum function, which is highly optimized. Similarly, functions like saply and maply can replace loops for applying functions to elements of a list or multiple vectors. The apply family of functions is particularly useful for row or column operations on matrices and data frames, offering a more efficient alternative to nested loops. By embracing vectorization, you can write cleaner code that runs faster, especially when working with large datasets. Parallel processing in R allows you to distribute tasks across multiple CPU cores, significantly reducing computation time for large-scale problems. The parallel package provides functions like McLaply for multi-core processing on Unix-based systems, while parlaply is suitable for Windows environments. The forEdge package extends this capability by enabling more flexible parallel loops. For even greater performance, you can explore GPU acceleration using packages like GPU-R or CUDA, which leverage graphics processing units for parallel computations. However, these techniques require careful implementation and are best suited for tasks that can be easily divided into independent subtasks. Adhering to best practices for optimization ensures that your R code remains both efficient and maintainable. Writing clean, readable code from the start simplifies the process of identifying and addressing performance issues later. After making changes to optimize your code, it is essential to test and validate the results to confirm that the improvements are meaningful. Striking a balance between readability and efficiency is crucial, as overly optimized code can become difficult to understand and maintain. By following these practices, you can create R programs that are not only fast, but also easy to debug and extend over time. In summary, performance optimization in R involves focusing on speed, memory usage, and efficient coding practices. Prioritizing vectorization, profiling, and parallelization can lead to significant improvements in code execution. By combining these techniques with tools like data table, apply functions, and parallel processing packages, you can achieve sustainable performance gains. Remember that optimization should not come at the expense of code clarity, and continuous testing is key to ensuring that your efforts yield measurable results. With these strategies, you can write R code that is both powerful and efficient. Efficiency in R refers to writing code that runs quickly, uses memory wisely, and is easy to read and maintain. When working with large datasets, inefficient code can lead to long processing times and excessive memory consumption, which can be problematic for both personal projects and professional applications. To address this, we focus on 3 key strategies. Vectorization, which allows us to perform operations on entire vectors instead of individual elements. Avoiding loops, which are generally slower in R compared to other programming languages, and leveraging built-in functions, which are often optimized for performance. These approaches not only improve speed, but also make code more concise and easier to understand. Vectorization is one of the most powerful tools in R for writing efficient code. Instead of using loops to iterate through elements, we can apply operations like plus, multiply, or sum directly to entire vectors. For example, adding 2 vectors together with the plus operator is significantly faster than using a for loop to add each element individually. This is because vectorized operations are implemented in C under the hood, which is much faster than R's native loop structures. By using vectorization, we can simplify our code while also taking advantage of R's optimized internal functions. This approach is especially useful when working with large datasets, where even small improvements in speed can make a big difference. Replacing for loops, and while loops with functions from the apply family can greatly enhance both performance and readability. Functions like laply, saply, and vaply allow us to apply a function to each element of a list or vector without explicitly writing a loop. For instance, laply returns a list of results. Saply simplifies the output to a vector or matrix, and vaply ensures a specific output type, which can help prevent errors. While these functions are generally faster than loops, there are cases where a loop might be more readable, especially in complex scenarios. However, for most tasks, the apply family offers a cleaner and more efficient alternative. It's important to choose the right tool based on the specific needs of the problem. Built-in built-in functions in R are designed to be both efficient and reliable. Instead of writing custom loops to filter or merge data, we can use base R functions like subset or merge. For example, subset allows us to select rows or columns based on conditions, while merge combines datasets based on common columns. Additionally, packages like deepler and data table provide even more powerful tools for data manipulation. The deepler filter function, for instance, is often preferred over subset because it offers a more consistent syntax and integrates well with other deepler functions. Similarly, data table is known for its speed in handling large datasets. By relying on these optimized functions, we can write code that is both faster and easier to maintain. Managing memory effectively is crucial when working with large datasets. One way to minimize memory usage is to avoid creating unnecessary copies of data. For example, using subset with the by reference argument in data table can modify data without duplicating it, which saves memory. Additionally, it's important to remove variables that are no longer needed using the rem function. This helps free up memory, especially in long-running scripts or when processing multiple large datasets. Finally, the GC function can be used to manually trigger garbage collection, which clears unused objects from memory. While R automatically manages memory, proactive use of these techniques ensures optimal performance. Profiling and debugging are essential steps in identifying and resolving performance issues in R code. The system time function provides a quick way to measure the execution time of a block of code, while micro-benchmark offers more precise timing by running the code multiple times and calculating averages. For more detailed analysis, the rprof function can be used to track which functions take the most time, and summary rprof helps interpret the results. These tools are invaluable for pinpointing bottlenecks in complex workflows. By regularly profiling our code, we can make informed decisions about where to focus optimization efforts, ensuring that our programs run as efficiently as possible. Following best practices for efficiency can make a significant difference in how our R code performs. One key practice is pre-allocating memory for large objects, such as using the vector function to create a vector of a specific size before filling it. This avoids the overhead of dynamically resizing objects during execution. Another important tip is to avoid unnecessary data transformations, such as converting data between different formats or types, which can slow down processing. Finally, using set seed ensures that random sampling is reproducible, which is critical for sharing results or testing code. By incorporating these habits into our workflow, we can write more efficient and reliable R code. Efficient R code is essential for handling large data sets and ensuring that our programs run smoothly. By focusing on vectorization, built-in functions, and profiling, we can significantly improve performance and scalability. Remember, writing clean and optimized code is not just about speed. It also makes our work easier to understand, maintain, and collaborate on. As you continue practicing, always look for opportunities to apply these principles in real-world scenarios. With consistent effort, you'll develop the skills needed to tackle complex data challenges with confidence and efficiency. R packages are essential tools in the R programming language that allow developers to organize and share their code, data, and documentation in a structured way. These packages act as self-contained units that make it easier to distribute and reuse code across different projects and teams. By standardizing how code is structured and shared, R packages promote consistency and collaboration, ensuring that everyone working on a project can access the same tools and resources. The core components of an R package include the description file, which holds metadata like the package name, version, and dependencies. The NAMESPACE file, which controls which functions are available to users. The R scripts folder, where the actual code is stored. And the documentation, which guides users on how to use the package effectively. These elements work together to create a cohesive and maintainable code base. Setting up the structure of an R package is the first step in building a functional and organized project. Developers can use RStudio's built-in tools by selecting New Project and then Package to automatically generate the necessary files and folders. Alternatively, the command line tool R CMD build can be used for more manual control. The package directory typically includes several key folders. The R folder for storing R scripts, the man folder for documentation files, and the inst folder for any additional resources like data files or configuration files. Proper file naming is crucial, as files like description and NAMESPACE must follow specific conventions ensure the package functions correctly. For example, the description file must contain accurate metadata, and the NAMESPACE file must define which functions are accessible to users. This setup lays the foundation for a well-organized and scalable package. The description file is a critical component of an R package that contains metadata defining its identity and requirements. This file includes fields such as the package name, version number, title, author, and license, which provide essential information for users and the R ecosystem. For instance, the license field specifies the terms under which the package can be used, such as the GNU General Public License, version 3. The description field offers a brief summary of the package's purpose, like a package for data analysis. Additionally, the description file lists dependencies, indicating which other packages are required for the package to function properly. Validating the description file with RCMD check is a vital step to ensure there are no syntax errors or missing fields, which helps prevent issues during installation and usage. This meticulous attention to detail ensures the package is both functional and user-friendly. The NAMESPACE file plays a key role in managing the visibility of functions within an R package. It determines which functions are exported, meaning they can be accessed by users outside the package, and which are kept internal for the package's own use. This helps avoid naming conflicts and ensures that only the intended functions are available to the end user. Developers can generate the NAMESPACE file automatically using the Relaxation 2 package, which extracts documentation comments from the code and updates the NAMESPACE accordingly. Alternatively, the file can be manually edited for more control over function exports by explicitly defining which functions are exported. The NAMESPACE file enhances the package's reliability and clarity, making it easier for users to navigate and utilize the package's capabilities. Writing functions and their documentation is a fundamental part of developing an R package. The Relaxation 2 package simplifies this process by allowing developers to write comments directly in the code, which are then converted into documentation files. For example, a function might include a Relaxation 2 comment like description. This function calculates the mean of a numeric vector. The comment also specifies parameters such as at param x, a numeric vector, to guide users on how to use the function. Once the comments are written, running Relaxation 2, Relaxationize generates the necessary documentation files, making it easy for users to access help and examples. This practice not only improves the usability of the package, but also ensures that the documentation stays up to date with the code, reducing the risk of discrepancies. Testing an R package is essential to ensure its reliability and correctness. The Test That package provides a framework for writing unit tests, which are small, focused tests that check individual functions for expected behavior. For example, a test might verify that a function returns the correct result when given a specific input, or handle edge cases such as empty vectors or invalid data types. Writing tests for both typical scenarios and unusual cases helps catch bugs early and ensures the package behaves as intended. After writing tests, developers can run them using Test That, test file, or integrate them into the RCMD check process. This step is crucial for maintaining the quality of the package and building trust with users who rely on its functionality. Building and installing an R package prepares it for distribution and use. The build process creates a distributable file, typically a tar GZ archive, which can be shared with others. This can be done using the command line tool rcmd build or the DevTools packages build function, which streamlines the process. Once built, the package can be installed using rcmd install or DevTools install, making it available in the R environment. Before distribution, it's important to resolve any dependencies, ensuring that all required packages are installed and compatible. This step prevents errors during installation and guarantees that users can seamlessly use the package without additional setup. A well-built and installed package is the final step in making the code accessible to others. Distributing an R package allows it to reach a wider audience and be used by others. One common method is submitting the package to CRAN, the Comprehensive R Archive Network, which hosts a vast collection of R packages and ensures they meet quality and documentation standards. Alternatively, packages can be shared via GitHub or other version control platforms, enabling collaborative development and easier updates. When distributing a package, it's important to provide clear instructions for installation and usage. such as how to install from CRAN or GitHub. This ensures that users can quickly and confidently start using the package, reducing barriers to entry and fostering adoption. Effective distribution strategies help maximize the package's impact and utility. Adhering to best practices when developing our packages ensures they are maintainable, user-friendly, and aligned with community standards. Following our style guides, such as those from the Tidyverse, promotes consistency in code structure and naming conventions, making it easier for others to read and contribute. Using version control systems like Git allows developers to track changes, collaborate effectively, and roll back to previous versions if needed. Maintaining a changelog helps users understand what has changed in each release, while clear and comprehensive documentation ensures that users can navigate the package's features with ease. These practices not only enhance the package's quality, but also foster a culture of transparency and collaboration within the R community. Our packages are powerful tools that simplify code sharing, reuse, and collaboration in the R programming language. By following the key steps of structuring the package, writing documentation, testing thoroughly, and distributing it effectively, developers can create robust and reliable tools for others to use. Mastering the art of package development not only improves the efficiency of individual projects, but also contributes to the broader R ecosystem by promoting reproducibility, transparency, and teamwork. As you continue to explore R, remember that building and maintaining packages is a valuable skill that can significantly enhance your ability to work with data and share your expertise with others. Documentation in the R programming language is a critical practice that ensures code remains accessible, understandable, and maintainable over time. When we document our code, we are essentially creating a roadmap for others, whether colleagues, future developers, or even our future selves, to navigate and utilize the functions we create. This becomes especially important as projects grow in complexity and multiple people contribute to the same code base. Well-documented code enhances readability by providing clear explanations of what each function does, how it operates, and what inputs it requires. It also improves maintainability, as it allows developers to quickly identify and fix issues without having to reverse engineer the code. Furthermore, documentation facilitates collaboration by ensuring that everyone involved shares a common understanding of the code's purpose and functionality. Finally, automated generation of help files through tools like Relaxation 2 ensures that documentation stays up to date with the code, reducing the risk of outdated or missing information. Relaxation 2 is a powerful package in the R ecosystem designed to simplify the process of creating and maintaining documentation for R functions. Unlike traditional methods that require writing separate RD files, which are manually created and maintained, Relaxation 2 uses inline comments directly within the code. This approach eliminates the need to switch between code and documentation files, making the process more efficient and less error-prone. By placing comments above functions, developers can describe their code in a natural, human-readable format that is automatically converted into formal documentation. This not only saves time, but also encourages better documentation practices by integrating them into the coding workflow. Relaxation 2 also seamlessly integrates with RStudio, providing features like auto-completion, syntax highlighting, and real-time previews of documentation. This integration makes it easier for developers to write, review, and update documentation as they work, ensuring that it remains accurate and relevant. The syntax of Relaxation 2 is straightforward and intuitive, making it accessible even for those new to documentation practices. Comments in Relaxation 2 begin with a hash and a single quote written as. This notation distinguishes them from regular code comments and signals to Relaxation 2 that the following text should be processed as documentation. Key tags are used to structure these comments and provide specific information about the function. The @title tag is used to define the function's name and a brief summary of its purpose. The @description tag offers a more detailed explanation of what the function does and how it works. The @param tag is essential for documenting each input parameter, specifying its name, type, and a description of its role. The @return tag clarifies what the function outputs, including its type and any additional notes. Finally, the @examples tag provides practical code examples that demonstrate how the function can be used in real-world scenarios. Together, these tags create a structured and comprehensive documentation system that is both user-friendly and machine-readable, Generating documentation with Roxygen 2 is a streamlined process that relies on the Roxygen 2 Roxygenize function. This function scans the code for Roxygen 2 comments and automatically converts them into RD files, which are the standard format for R documentation. To use this feature, developers place their Roxygen 2 comments directly above the functions they are documenting. This placement ensures that the documentation is closely tied to the code it describes, reducing the likelihood of discrepancies. Once the comments are in place, running Roxygenize triggers the generation of help files, which can then be included in R packages. This automation is a game changer because it eliminates the need for manual updates, ensuring that documentation remains consistent with the code. Additionally, as the code evolves, developers can simply update the comments, and the documentation will be regenerated automatically, saving time and reducing errors. The documentation generated by Roxygen 2 is highly versatile, as it can be converted into multiple formats to suit different needs. One common output is PDF, which is produced using the rcmd RD to PDF command. This format is ideal for sharing documentation in a printable, structured way, making it suitable for users who prefer physical copies or need to reference the material offline. Another option is HTML, generated with rcmd RD to HTML, which provides a web-friendly format that can be easily navigated and searched. This is particularly useful for online documentation or integration into websites. Additionally, RStudio offers an interactive help system that allows users to access documentation directly within the IDE, providing a seamless experience for developers. By supporting these diverse output formats, Roxygen 2 ensures that documentation is accessible to a wide range of users, from those who prefer printed materials to those who rely on digital tools. Adhering to best practices in documentation ensures that the resulting material is both effective and user-friendly. One key principle is to keep descriptions concise yet informative, avoiding unnecessary jargon while providing enough detail to guide users. Consistent formatting is also crucial, as it makes documentation easier to read and understand. For example, using the same structure for parameters and return values across all functions helps users quickly locate the information they need. Including examples is another vital practice, as they demonstrate how functions are used in context, which is especially helpful for beginners or those unfamiliar with the code. It is also essential to update documentation in tandem with code changes, ensuring that it remains accurate and relevant. Finally, leveraging RStudio's Relaxation 2 templates can significantly enhance efficiency, as they provide a structured starting point that reduces the time and effort required to write documentation from scratch. Relaxation 2 is an indispensable tool for anyone working with R, as it simplifies the documentation process and improves the overall quality of code. By making documentation an integral part of the coding workflow, it encourages developers to create clear, well-structured, and maintainable functions. This, in turn, enhances the user experience by providing accessible and reliable information about the code's functionality. For package development, Relaxation 2 is particularly valuable, as it ensures that documentation meets the standards required for distribution. It also fosters collaboration by making it easier for multiple developers to contribute to a project without confusion or miscommunication. Ultimately, Relaxation 2 supports the creation of a code base that is not only functional, but also reusable and sustainable, laying the foundation for long-term success in R programming. R Markdown is a powerful tool that allows users to seamlessly integrate code, text, and results into a single, cohesive document. This means that instead of switching between different applications or manually copying and pasting outputs, you can write your analysis, run your code, and present your findings all within one file. By combining R code with narrative text, R Markdown enables reproducible research, which is essential in modern data science. Reproducible research ensures that your analysis can be easily replicated by others, fostering transparency and trust in your findings. The flexibility of R Markdown lies in its ability to generate output in multiple formats, including HTML, PDF, and Word, making it accessible to a wide range of audiences. Whether you are preparing a report, a research paper, or a presentation, R Markdown provides a streamlined workflow that adapts to your needs. The key components of an R Markdown document include the YAML header, Markdown text, code chunks, and dynamic output. The YAML header serves as the configuration section at the beginning beginning of the document, where you can define the title, author, and the desired output format. This section is crucial for setting the structure of your final file. Markdown text allows you to write plain text with simple formatting options, such as headings, bullet points, and links, making it easy to create readable content. Code chunks are where you embed our code to perform analysis, generate visualizations, or compute results. These chunks are enclosed in triple backticks and can be customized with options to control their behavior. Dynamic output ensures that whenever you modify the code, the results in your document update automatically, eliminating the need for manual recalculations. This feature is particularly valuable when iterating on your analysis or making adjustments to your code. Creating an R Markdown document is straightforward, especially if you are using RStudio. To begin, open RStudio and navigate to the File menu. Then select New File and choose R Markdown. This action will prompt you to select a template, such as a default document, a book, or a report, depending on your project requirements. Once the template is chosen, you can start writing your content using Markdown syntax, which is simple to learn and highly versatile. You can insert R code chunks wherever needed to perform calculations or generate visualizations. For instance, if you want to summarize a dataset, you can write a code chunk with the summary function. Finally, to generate the final output, simply click the Knit button. This action will execute all the code in your document and compile it into the chosen format, such as HTML or PDF, ready for sharing or publication. Integrating R code into an R Markdown document is a core aspect of its functionality. To add code, you use triple backticks followed by the language identifier, such as R, for example. Writing R summary cars will execute the summary function on the cars dataset and display the results. You can also customize code chunks with options like echo equals false to hide the code itself while still showing the output, which is useful for creating clean reports. Inline R code allows you to dynamically insert results into your text, such as writing R mean cars $speed to show the average speed